Among another, and has organized multiple scientific events like this. He's a IEEE senior member and IFAC member of technical committees. TC 1.2, Adapting and Learning System, Mechatronic System, Robotics, and Marine System. You are welcome.
Thank you very much for this nice introduction, and good morning, everybody. So it's my big pleasure to come again to Mexico, as anytime I am very, very honored to come back to Mexico. Concerning this summer school, as they explained before, Dr. Hipólito, that it's the 3rd edition. We started this like 3 years ago, starting from just a very simple idea. They invited me here for a few days, and from this idea of invitation, we transformed this with Jorge to a summer school. Then it was very successful. We organized the 2nd one. It was very successful, and now it's the 3rd one, and we are now planning the next one. So it's very nice. We are continuing working. The lectures, there are several lectures during the 4 days of this summer school. And the last lecture is really like applied. So we will do something on MATLAB to apply what we learned during the first lectures. And since the summer school concerns control of complex robotic systems, so I choose to introduce actually, or to give you an overview about the status of robotics today. And this is the topic of this first lecture. And the other 5 lectures, they will be on control or complex robotic systems. And for each lecture, we will be interested in a specific application. We will be interested in underactuated robotic systems. Then we will talk about underwater vehicles. We will talk about parakinematic manipulators, exoskeletons, humanoids, and so on. And the last lecture, it will be on the application using MATLAB Simulink as a last lecture, lab course. So regarding this first lecture, so we will try to give you an overview about robotics today. So first of all, let me introduce myself and introduce my research lab in France. Actually, I'm coming from Montpellier. As you can see from this picture here, you can see the map of France. And Montpellier, it's a city situated in the south of the country. So it's a very nice city. And Montpellier is very well known by a lot of things. Now I will try just to introduce maybe 2 or 3 things regarding Montpellier. So the first thing is, you know, the oldest faculty of medicine in the world that was founded like more than 800 years ago. It is situated in Montpellier, and it's continuing active training the students in medicine. So this is the first thing to know about Montpellier. The second thing to know is that Montpellier is the 8th biggest city in France, and with a population of more than 300,000 people. And a big part of this population are students, because almost more than 70,000 people, they are students. And it's almost 25% of the population are students. And Montpellier also is known by something, as you can see from the video here, we see sun throughout the video. So we call Montpellier the city where the sun does not set. And according to the statistics, we have every year more than 300 sunny days. Now our research lab is called LIRM and is coming from a laboratory of informatics, robotics, and microelectronics, and it is situated in the north of the city. It's on 2 buildings. One is near each other. This is the old building. This is the new building, and also our research lab. So we made research in computer science, robotics, and microelectronics, and we are belonging to 2 institutions. So the first institution, it's the University of Montpellier, and as any research lab in the world, so we belong to the University of Montpellier. However, something which is maybe specific in France, that we have the National Research Council, CNRS. And it means that this research lab is between these 2 institutions. It means that we have senior researchers from CCRS and also faculty members from the University of Montpellier, all together working in this research lab. We are more than 440 people in this research lab, and we are organized in 3 research departments, and I'm working in the Department of Robotics. So this is now, after this short introduction of my research lab, this is just the outline of this first lecture, and so I will try to give you an overview about robotics today, and we will start with the status of robotics today, where we can find robots, okay? And what we can notice is that we have more and more robots in the society of today. Then we will go back to the origin of robotics to understand when it was started, robotics developments. And then we will give you some basic definitions to understand what is a robotic manipulator, and then a classification of robots to be able to distinguish between a robotic manipulator, an underwater vehicle, an air vehicle, and so on. So this classification is very important to understand the rest of the presentation, where I will focus on different aspects and different applications in robotics, and for each of them I will show you the general context, why we are using robots for those applications, and what are the main challenges. And for each of them, I will show you a short video to be aware about what we are doing nowadays. So first of all, what we can notice nowadays that we have more and more robots, and they are very close to our society. We have more and more robots in our society. Here it's just a short video. I have been in Thailand a few years ago, and we were visiting a research lab there. And for the dinner, the professor invited us to go to a restaurant, and he proposed us a Thai restaurant or a Japanese restaurant, and we chose the Japanese restaurant, and we were surprised when we arrived to the restaurant. So you order what you want to eat, and a few minutes later, you will see robots bringing the food for you. And 100% of this restaurant, so they are using only robots to bring you the food, as you can see in this short video. And from this short video, we can notice that we have more and more robots. They are not in the industry here from this application, they are not in the research labs, but they are in the society. They are in this public space, which are restaurants. So this is the first thing that we can notice about robotics today. Now let's go back to the origin of robotics, because nowadays robotics is a very rich field of research and industry. And let's go back to the origin of robotics. And it goes back to more than 1,400 years ago, where the idea here, it was to design an auto-regulated system, where actually we want to measure the time. It's a water clock, and it was designed by Greek engineers. And here is the basic principle. And the basic of this system, it's an auto-regulated mechanical system, hydromechanical system if you want, and the idea here, it's very easy. At that time, they want to do the regulation of the flow of water here as the output of this first phase. So nowadays, if I ask you to do something like that, it's very easy. You can put just here a valve, an electro valve, and then you can control the flow of water. It's very easy. However, at that time, you can imagine you do not have anything. No electricity, no technology, no sensors, no actuators, nothing. However, despite this, they succeed to control perfectly the flow of water here as the output of the first phase. And they obtain this based on the law of physics. If you look at this first phase, if you can keep here the height of the water constant, it means that the pressure here is constant. It means that the flow is constant. So the idea is just to put here a hole to evacuate the water when you reach this height. It means that here the height will remain all the time constant, and the pressure is constant, and the flow here as the output of the vase is constant. So they are regulating the flow of the water in automatic way. And this small person here is moving up here, indicating the time with precision on this cylinder which is rotating in front of him. So this is the basic principle of the first robotic system in the world, where we are controlling the flow of water. And if you analyze this system itself and you compare it to any robotic system of today, you can notice that we have all the main components of any robotic system. It means that you have sensors, you have actuators, you have the control system, and you have the mechanical structure. Everything is here, but it was designed with a mechanical way. So this is the first idea. Then we can find the works of the Arabic engineers. One of them is this guy. He's called Al-Jazari, and he designed a lot of auto-regulated systems, also based on hydromechanical systems. Then we can find the works of Leonardo da Vinci, around 95, sorry, where he imagined a lot of kind of robots, but the problem at that time, it was also the technology, so he was not able to construct those robots. It means, like, for instance, he was the first one who imagined a humanoid robot in the world, but he didn't construct the robot because of the technology at that time. Then we can find the work of other engineers. One of them is Duvo Consol. This guy, he's from Grenoble, and he designed this automatic tag. It's around 1738, and up to 1921, all what we constructed here, we don't call them robots. You know why? Because we don't know the robot yet, the robot term yet. We didn't define it. So it was introduced for the first time around 1921 by a fiction science writer called Charles Chapek, here on the picture. He used the term robot for the first time in the world in this play that was prepared in Prague in 1921 and played in New York in 1922. And between 1921, where we introduced the term robots, and 1941, we can imagine that we had a lot of stories where humans are exploiting robots, and by the end of the story, as you can see in the movies, the robots will go against the humans. Until 1941, with another fiction science writer, Asimov, where this guy introduced the 3 laws of robotics. And also until this date, we didn't construct a real robotic system, a real robot. So the first time that we introduced a real robot in the world, it was around 1961. So with the patent of this guy, George Duval, he wrote the patent around 1954, and 1961, the General Motors, the car manufacturer, they bought the license and they manufacture this robot and use it in the car manufacturing society. And starting from that date, the robotics start to be developed. And with the progress of electronics, of computer science, of computers, sensors, actuators, and AI nowadays, so robotics becomes nowadays a very, very rich research field. This is just a short video that shows you also the different milestones with the constructions of the first humanoid robot, like here around 1495 with the Da Vinci, 1645 this machine, the Duck of the Gonson, 1709, and a lot of kind of robots constructed during that period. Here, this is the first robotic system which is constructed based on parallel structure, and it was a painting system. This is a mobile robot that was designed 1948, 1954. This is the first patent of this first industrial robot in the world. This is a walking robot. This is a humanoid walking robot also. It's a biped. 1969, 73, we continue working on walking robots at that time also. And also sometimes you have some snake-like robots. I will introduce this in this lecture also, soft robotics nowadays, and a lot of kind of walking and robotic machines. This is an underwater walking machine that was designed to walk underwater. So it's an underwater walking robot, and also bio-inspired underwater vehicles, humanoids again, and also for space we use also rovers or mobile robots. And then also the development of the social robotics nowadays, we develop a lot of kind of robots. So a short video regarding this first industrial robot.
The industrial robot has a family tree. Its roots are firmly planted with this man. George Duval is known as the grandfather of robotics. It was his patent, filed in 1954, that was the blueprint for the machine that would revolutionize industry.
This is
It took years of development and fundraising, but George Duval's blueprint
this is the robot itself.
in 1961. The new company was called Unimation. The robot was named Unimate. That same year, General Motors bought the first Unimate and put it in a New Jersey plant to take
applications
parts from a die casting machine.
Where we use this.
Automation was not new to the automobile industry, but this was something different. The Unimate created the definition of an industrial robot.
Example of applications.
Even labor unions endorsed robots. recognizing the inevitable increase in
This
productivity.
is in car manufacturing.
But the original
tasks.
Unimate with an $18,000 price tag remained a tough sell.
And at that time, the price was 18,000 US dollar, which was very, very expensive at that time. Now let's start with very basic definitions, because you are coming from different fields. Let me introduce basic definitions, and let's start with a robotic manipulator. So what is a robotic manipulator? And since it was the first one designed in the world, so a robotic manipulator, this is what you can see on this picture on the right, and which is something inspired from the human arm. We can say also it's a robotic arm. If you analyze the structure of the human arm, what we can find here, we can see like the joints or the articulations. It's with the same way we define articulations also in robotic system. In the human arm, how we can move the arm. So we use the muscles. And the case of the robotic manipulator, so we will put what we call them actuators or motors to replace the human muscles. In the human arm, we have here the bones, and they are replaced by the bodies that are represented here to link to each two joints together. And then here in the human arm, we have the end to manipulate objects. And the case of a manipulator is the end effector, where you have to place the good tool depending on the task that you want to do. And for robotics, we construct different kind of joints or articulations. The first one, which is represented here, it's a pure rotation. So you have one body rotating with respect to another one around this axis. Then we design also different kind of articulations. This is a prismatic or translational articulation. Then we can have articulations with 2 degrees of freedom. Since the two first here, they include just 1 degree of freedom. This one is universal joint, which includes 2 rotations combined, and the last one here we combine 3 rotations. It means when you construct your robotic system, you have to choose among those articulations to design your robotic system. If you look to any robotic system, the basic structure can be represented by this picture, as you can see. So we have mainly 4 main components. So the first one is the mechanical structure, as you can see here. You construct it based on choosing the joints, choosing the bodies, the materials, the end effector, and so on. However, the mechanical structure itself cannot move. To be able to move the mechanical structure, you have to put actuators in the joints. And then if you put actuators in the mechanical structure, it's not enough, because when you move, how you decide when to stop? You have to put sensors here to detect the robot status and also the environment. So we use the sensors, and all this is not enough, because if you want to control the motion of any robotic system, you have to design controllers, and you have to implement those controllers, and to implement them, you have to choose a control system. It can be computer, microcontroller, or anything else. So if you analyze any robotic system of today, you will find all the time these 4 main components, including the 4 parts that I just presented here. Now, if I ask you the question, what would be the difference between a mobile robot and a robotic manipulator? And what is the difference between an underwater vehicle and a drone? So maybe the answer itself is not easy from the beginning, but if you understand this classification that I introduce here, you can distinguish any difference between 2 robots. Let me start here. Here we have robots, and then we can have 2 big classes of robots. So the first one is the class of robotic manipulators, and the second one is the class of mobile robots. What's the main difference between them? The first class of robotic manipulators, the base is fixed. It means that, what means this? It means that here when you construct a robotic manipulator, the base is here, it corresponds to the shoulder of the arm of the human, and this is fixed, it does not move. You have to move just the joints through the actuators to move the end effector depending on the task that you want to do. And if you look to this first class, we can distinguish 2 subclasses. This is the class of serial manipulators and parallel manipulators. What is the difference between them? A serial manipulator is constructed a structure like a human arm. It means that you have a joint, a body, joint, body, joint from the shoulder until the fingers. So this is the structure. This is why we call them serial robots. And nowadays we can find also flexible or soft robots based on this structure. And the second one, parallel robots, they can be constructed if you take like a serial manipulator, a second one, and you connect them, so you obtain a parallel robot. So this is the structure, and then depending on the number of these kinematic chains, here for instance you have 4, here you have 6, it can be 2 or 3 or 4 or 6, no problem with this, but all of them, they are in parallel. This is the case of parallel manipulators. So this is first class. Then we move to the class of mobile robots. For the class of mobile robots, so we will remove this constraint of the base is fixed. The base can move. If you have an object and you ask the object to move, you want to make the object move in the space. We have 3 options. So the first option, we stay around the ground. So we have mobile robots, ground mobile robots. The human created the wheel, and we have wheeled mobile robots. They are equipped with wheels, actuators, and they can move on the ground. They stay in contact with the ground. However, the human created something else, because we can have a bio-inspired locomotion system based on the legs, like the humans. When we move, we use the legs, and we can be inspired from the human, from the insects and animals, and we construct what we call them legged robots. And depending on the number of legs, we can have bipeds with 2 legs, quadrupeds with 4 legs, or 6 legs with the case of hexapods. So this is the ground robots. Now I come back to the question, if you move an object in the space, the first one we stay on the ground, the second case we can make the object diving inside the water. And this is what we call underwater vehicles, and for underwater vehicles also the same, the human created something to move underwater, a locomotion system based on the propellers. A propeller, it's a motor that is rotating a thruster, and we can use a certain number of thrusters to equip the underwater vehicle to move inside water. However, also the human tried to create something which is bio-inspired, like sea animals, like fish, for instance, turtles, and so on. So they move underwater. They do not have a propeller, but they have fins. So we can design robot based on fins to move underwater. So this is second class, and the last class, which is possible to move, it's to move in the air. And we have aerial robots or aerial vehicles, and the same, either we can use propellers or we can design aerial vehicles that can fly based on the wings. So this is the general classification, and also pay attention, this is only the basic classes of robots. So now if I go back to my question, what is the difference between a mobile robot and a robotic manipulator? It's very easy to answer now, because you have the information. The difference is that here it's a mobile robot, so the base is not fixed, so the robot can move on the ground. Here the base is fixed, and it's a manipulator, and we can move the end effector to do a specific task. Now the other question is, if I want to move on the ground, and I want also to manipulate objects, how I can do? In this case, the solution will be to combine 2 robots together to obtain this. And here you have 2 examples. One ground vehicle equipped with a parallel robot here, and one aerial vehicle equipped with a robotic manipulator. So we can find also different kind of robots combining 2 structures or more. However, also, if you look to this classification, whatever your robotic system is, if you look to the main components, you will find the 4 main components that I explained before. Take an example, let's take like the mobile robot. So you have mechanical structure, we have the actuators, the motors, we have the sensors to measure the environment, and we have the control system. So all the 4 components, they are here. And any example here, you can find the same main components. Now let's go through the research and applications of robotic systems. And nowadays, it's just to say that robotics is extremely rich. It starts with industrial applications like car manufacturing. However, we have a lot of other fields of robotics like medical robotics, humanoid robotics, space robotics, underwater robotics, mobile robotics, micro robotics, and so on and so on. A lot of fields. And now let's try to have a look to all of them, or most of them, the most important of them. And let's start by the first one, which concerning industrial robotics. And industrial robotics, I will show you a short video, and it's coming from KUKA. And KUKA is one of the biggest biggest companies manufacturing robots, and with several applications. We will see first, this is a company in Germany. Here, as you can see, they are constructing the robots. So we use humans especially for specific tasks where we need very high precision to manipulate objects and to do the assembly, for instance, like painting, for instance. And then once the robot is constructed, you have to make some computations, at least do some simulations, to identify the parameters of the robot itself, and then we will see where those robots are used, because they are extensively used in several fields of industry, and they are very performant. This is why we use them. A classical example can be the car manufacturing tasks for the assembly in car manufacturing, and it's not the only application, because a lot of applications in industry, they need high speed, sometimes they need high precision, they need sometimes high speed and high precision, and sometimes you have to manipulate objects which is very dangerous for the human, and sometimes you have to move very huge or heavy payloads, and this is not very easy with the human also, and so on. Sometimes you have to do the machining, and also to obtain very nice pieces obtained by machining, so we can use this kind of robots. So they are used in more than 25 sectors and a lot of countries, and also they are used for different applications where we need sometimes the cooperation between two robots to move something. Industry of metallurgy, where it's very dangerous for the human worker. Here the cooperation between two robots and other general applications, as you can see here. And also in industry, this is the previous video, it was on serial robots. Now parallel robots, where they are used. Look here, this is a parallel robot. It has a parakinematic structure. This is the cabin, and inside the cabin you have the pilot. So this is a flight simulator, and the flight simulator is used for pilots to do a training. And how it works, the pilot is inside the cabin here, and here, as you can see around, you have the screens, and we are here reproducing the dynamics of a real airplane. And the control actions here, manipulated by the human or the pilot, they are connected to the motion of the robot, and here, for instance, they are simulating takeoff. And look, if you have been in an airplane before, when it starts accelerating, you have this sort of vibration, and even this, we can see it in this video, in this motion. So this is one of the main applications where this kind of robots, they are used, because they can carry a heavy payload. This is why they are used for this application. The second case, or the second application of parallel robots, this is another structure. It's what we call lightweight parallel robots, and they are used for food packaging. As you can see, the idea is to pick objects coming on a belt and put them in a box, and to do this as fast as possible. And you have to increase the speed and the acceleration to increase the productivity in industry. And those robots, all of them, they are parallel robots. It starts with, like, by the mid of 80s, like 1985, by the Delta robot developed by Clavel at EPFL, and nowadays we have much more kind of robots. Now, what is mobile robotics? So the idea is to design a robot like that with wheels, and the idea is to equip the robot to be able to do the perception of the environment. And in the environment perception, you can be able to do the mapping, the slants, localization mapping together, as you can see here, and you obtain the map like that. Sometimes we can use different kinds, like trucks here, to equip your robot. Sometimes we need to equip the robot with a manipulator, because we have to do manipulation, or here, the two arms to do manipulation, and sometimes we can design a small robot controlled by a smartphone. Let me show you a short video to understand how it works, these kind of robots, and where they can be used. First of all, as you can see, they can move in the environment, and also they rely on the sensors that they have, and they are able to detect the obstacles. So once you acquire a robot like that, and it's coming also from KUKA, the same manufacturer of manipulators, so you acquire a robot like that, the first thing to do is to do the SLAM. This simultaneous localization mapping. You have to move your robot in your environment, and the robot, based on the sensors, as you can see, he will be able to detect the walls. As you can see here, the walls, and it constructs, and here it's saving the data, and it is constructing the map. Once you construct all the map, you will know the area perfectly, and then you can do an automatic or an autonomous mission. Say here you are constructing the map, you have an obstacle, you avoid the obstacle, and you are controlling the robot by the human, like manually. And you save the map, and you have the map here constructing the map. Once the map is constructed, you can start here planning a mission. I want to move from point A to point B to point C, and this is the environment that you construct. And the idea is to do this in an autonomous way. It's not to be controlled manually, but in an autonomous way. During the execution of the mission, if the robot will encounter another obstacle, is another robot moving, he will decide to stop here to avoid the collision between the robots here and in an autonomous way. Once the obstacle is no longer here, we will continue, we reach the second point here. The map here has been changed. It's no problem. We can recompute the new path to reach the target. And we continue the motion in real time based on the sensors and the perception of the environment. Once the robot detected an obstacle and he can avoid the obstacle like that, he can change slightly the path to avoid the obstacle. So this is just an illustration of mobile robotics, how it works, how we can construct the map, and how we execute the mission. Another field in robotics is called the bio-inspired robotics. And the idea is to get inspiration from animals, nature, insects, and so on. And we call this field biomimetics. If you want, for instance, to be interested in bio-inspiration from the nature, we can have a robot design which is bio-inspired. We can have the control design which is bio-inspired. We can have an actuator or a sensor which is bio-inspired. And also we can have a locomotion which is bio-inspired. Let's take this last example of locomotion. For locomotion, as I explained before, we have three possibilities. We stay on the ground, we can here go to in the air, or underwater. For the first case, so the human created the wheel as a good locomotion system for on the ground. However, for bio-inspired locomotion, we will forget about the wheel and we will use something else. So we use the legs as the animals, as you can see here. Some of the animals, like snakes, they are limbless. They do not have limbs, and they can move also by twisting the body of the robot. Now let's go in the air. Also the same, the human created the propellers, and for bio-inspired, we will not use propellers, and we use wings, and you have here an example of flapping wings of robots which are bio-inspired from birds. Then the last case, underwater vehicles, the same, we use classical propellers designed by the human. For the bio-inspired, we will not use them, and instead of them, we'll use fins. Now, let me show you just a short video. Here, just some examples of bio-inspired robots, and I will show you a short video.
Started in industrial settings where very precise and fast motion was needed. Those same technologies are not really suitable for interacting with people.
When we think of biorobotics, we really think of something that's more like the field of AI, of artificial intelligence. Thinking about that combination of both the body and the brain and, the group. There's just a lot of examples in biology where we can see how that can be achieved and how we can leverage the same kinds of ideas.
I think biorobotics is a new discipline connecting living creatures and robots.
So if we look at nature and see how nature does things,
looking at design principles in nature and trying to build robots that either implement those principles or interact with those principles.
looking at humans, looking at biomechanics, looking at the materials that exist in nature, looking at the algorithms that nature uses.
What is intelligence? What is the technology that's going to make us be able to understand what biology already has?
And hopefully it's not just inspiration, but actually bio-informed, that we take what we learn from animals and use it in applying those techniques to robots.
So there is a company in Germany called Presto. They designed a lot of bio-inspired robots. Let me show you just some of them. The video is slightly long, but I will show you just some of them. And the first one here, it's an underwater vehicle which is bio-inspired. It uses fins, undulating fins, to move underwater. As you know, so any classical underwater vehicle, it uses a propeller. Here, it does not use a propeller. So here, the body is constructed by soft materials, so it's flexible. This is the first thing. And then, as you can see here, the fins, they are moving by undulating the fins that push the vehicle here forward. And here, one of the applications, for instance, it can be the inspection of pipelines. You can use this underwater vehicle to go inside the very confined environments, and then you can control the motion of the vehicle. And then, depending on the task, if you are doing inspection, for instance, or perception, you can equip the robot with the right sensors to get the measurement. Suppose that, for instance, you want to do the inspection of a pollution inside a space, inside the lake, for instance, you can use this kind of robots. And here, the motion itself, as I told you, it uses here fins, and the fins are undulating to move the body inside water. Nice, let's move ahead. Now let's talk about legged and humanoid robots. And the idea of humanoid robots, it's like to design robots based on the morphology of the human. It means that you have the body, we have the legs, the arms, and the head. We have a lot of examples throughout the world, a lot of here Japanese examples, here from Honda also. They designed a lot of robots, from Boston Dynamics also. Some of them, they are using just 2 legs, 4 legs, 2 legs and 2 wheels, and so on and so on. And we will see also the case of androids. Let me show you 2 short videos to see some examples of those robots. And let's start with Boston Dynamics. There's a design. This robot is called Big Dog. And this Big Dog, it's a robot that was designed for like exploration of nature environments like that, where we have the direct interaction between the robot and the environment, where the environment is very complex. It can be the robot can be disturbed by an external disturbance here. It's pushed by the human, and here the ground is slipping, and the robot can manage the contact with the ground, can manage the balance, can keep its equilibrium. As you can see, it's very, very slippery here. Even for the humans walking on the snow, it's difficult. Imagine for a robot like that working on the snow. And those robots, they are equipped with very strong actuators, sensors to measure the attitude of the body, and also strong controllers to control the motion of the vehicle. And this vehicle can be used for several applications. So this is different situations where robot can be used. So it can be the inspection, it can be go to the natural environment like that, where the environment itself, it's very, very complex, and it's not so easy to manage this perception of the environment and also the motion, and keep balance and keep stability and dynamic walking and so on and so on. So this is the first example. The second example now, I will show you another example which is very amazing. And nowadays it was designed by this company, it's called Unitree. I will show you 2 examples. The first one, it's this mobile robot, which is a quadruped. It has 4 legs, but it has also wheels. And they combine 2 locomotion systems. The first one is the leg, and the second one is the wheel. And by combining both of them, let's see the performance that they can reach. As you can see, the motion is very amazing. It can move in an environment, very complex environment. As you can see, very high-speed motions, manage the equilibrium, the dynamic motion, and the robots can move in the environment using, at the same time, the legs and also the wheels. And they combine, so the motion of the legs of the wheels, depending on the necessity. If it is an environment where they need to use the wheels, they use the wheels, and sometimes they combine also the motion of the wheels with the motion of the legs, or the control of the joints of the legs. And here some examples where those robots can be used. So this is an example here. As you can see, it's very complex to go through these environments and to avoid obstacles, and also to move in this manner. So this is one example. I will show you another example from the same company, and now it's the humanoids. The same company is called Unitree, and humanoid robotics, one of the big problems is the dynamic stability of the walking, for instance. However, here they are, as you can see, doing very complex motions. The most important thing is to keep balance, is to keep the equilibrium of the dynamic motion. and also to coordinate the motion of the legs. So they rely on the sensors, on the control system. They use the AI, they use a lot of things to control the vehicle, and as you can see here are the performance that they can reach. If we want to go further, we have robots that are like humanoids. However, they have also aesthetically like the human skin. So as you can see here, the face is like a human. Those robots, we call them androids. And they can be used for several applications.
Our goal is to promote and to put to use
for
various
social robots.
robots that can be useful in a large range of fields in society.
So here it's able to read information from a paper. Nice. Now aerial robotics. So the idea of aerial robotics is to design aerial vehicles like that without a pilot, autonomously working. And now we have the case of quadrotors, and much more now we try to be interested in manipulating objects, not only equipping a camera on the quadrotor and take pictures, but sometimes we need to do manipulation of objects. And some examples, like for the rescue applications or for the delivery, so the drones, they are very promising solution. Let me show you also two videos to understand how it works.
I hold the spark in my hand and I press the power button twice. Spark starts looking for a pilot, and now that it recognizes me, it will automatically take off from my hand.
Starts.
Within seconds, I can get the spark in the air. Now, it's flying, but I need to control it. I want to angle it around to get just the right shot that I want. So to do that, we designed an interface using the simplest control interface that we could think of. And it's not your smartphone. Take a look.
So he will control using just the hand. Look, like gestures, and the drone will follow the motion of the hand of the human. So
just using my palm, I can move spark left, I can move it right, I can use it up and down, I can push it away from me, and I can pull it towards me. It's that simple to control, and it truly feels like magic. Now, within this range, I've got about 3 feet between me and the spark, but that doesn't show the epic perspective that drones are known for. So in order to get that perspective, I'm going to tell Spark to fly a little bit further away from me, and I'll do that by waving. Just like that, Spark flies about 10 feet away from me and keeps me centered in the middle of the shot.
So it's just an illustration. Let me show you another example which is very interesting. It's a rescue drone. Imagine that you are in a situation like that and you want to ask for rescue. So she is calling, and look how it works. So it's a demonstration, it's not really live, but it's a demonstration, but they show the ability where we can use drones for this kind of applications of rescue. And the good thing is that the drone can move in a straight line, and in a few minutes here, it will arrive, few seconds. So the drone arrives, and then she will get the drone, and she will follow the instructions of the doctor from the other side. So based on the communication between the lady and the doctor. Here, as you can see, a camera on the drone, and she will follow the instructions for this rescue task. This is just demonstration, and they call it a rescue drone. And the most important thing is the time, as you can see here. Nowadays, if you have a problem, you call the ambulance, you have to wait maybe for 30 minutes or 20 minutes to come. Here, in 2 minutes, the problem has been resolved. And here they show the importance or the advantage of using this technology for rescue tasks. Nice. Let's go ahead now, space robotics, and also, as you know, for the exploration of Mars and other planets, we use a lot of robots. One of them is this kind of robots. We call them rovers. Let me show you also a short video to understand.
This is the Mars rover Perseverance, the most advanced robot to land on another planet. In this video, we'll take a look at how it was built, the Atlas V launch, the journey to Mars, and the scientific instruments that allow it to study the surface.
So it's a mobile robot with wheels, it's a rover, and you'll see how it works.
This video is sponsored by Morning
And
Brew.
how they launch it, when it reaches the Mars, how they deploy it.
On February 18th, 2021, the Perseverance rover successfully touched down on Mars. It cost a total of $2.5 billion. It has many scientific instruments to help study Mars, search for signs of life, and prepare the way for future human explorers. Perseverance is, of course, not the first rover to visit Mars. Sojourner was in 1997, a very small rover, and here's a person for size comparison. Spirit and Opportunity in 2004, these were identical rovers sent just a few weeks apart from each other. Curiosity landed in 2012, and then Perseverance in 2021. Same size as Curiosity, but much more advanced technology. This is not a complete list. This just shows the most recent rover sent by NASA in the United States. For most of this video, I'll be focusing on Perseverance. NASA designs and builds the rovers in Pasadena, California at the Jet Propulsion Laboratory, or JPL for short. This took about 8 years of designing, building, and testing to get Perseverance ready to go. It was built in a clean room. It's free from dust or other contaminants. It's designed to work on another planet, different atmosphere, different gravity, and most of all, no repair station. It has to be engineered so well that it can last for years on its own. On top of that, it has to be light and compact so it can fit inside of the launch vehicle. Once it was ready to go, the rover was carefully packaged up and then flown across the United States to Kennedy Space Center in Florida. This is where the launch happened, the same place that NASA has been launching rockets since the 1960s. Perseverance was installed along with several other components that went along for the journey to Mars. We'll talk about each one of these pieces later in the video. This was all put inside of the payload fairing, then taken to the rocket, and then lifted up to the very top. This rocket is called an Atlas V. It's made by a company called the United Launch Alliance, or ULA for short. Let me point out that the rover was actually upside down for the launch. The best time to launch to Mars is about every 26 months. If we show this with the correct scale, you can barely even see the sun. For this animation, I'm going to show this out of scale so we can see this a little better. For the Earth to get around the sun, it takes exactly 1 year, right? No surprises there.
Anyway, so next field now is agricultural robotics, and for agriculture, the same. If we look back like 20, 30 years ago, we use humans for agriculture mainly, then we start developing like machines like that, controlled or piloted by the humans, but nowadays we design robots which are autonomous. Let me show you two short videos. One of them is the University of Sydney here, and they designed several robots. They are autonomous for several applications in agriculture, like harvesting, for instance. They are equipped with different sensors, like here the camera, and then the control system, and then the idea is to optimize these tasks in agriculture. And as you can see, the detection of the fruits, for instance, the gripping of the fruits, using a gripper, which is soft gripper, and then different kind of tasks. Another example here, it's another mobile robot which used also for agricultural applications.
Eindhoven is a self-driving reading robot. The setup is easy on the field via any common telephone, tablet or computer. It can reuse the field information, for example, the GPS data of the plant. The robot is costing between 25,000 and 30,000 euros.
Depending on the task you have to equip your robot, depending on the task that you want to do in agriculture. Nice. Now micro-robotics, imagine that I ask you to create a robot. And I want to ask you a robot, very, very small robot, like 1 by 1 by 1 millimeter. So the big problem is not in the idea itself. The idea itself is very easy. You can use the same structure as any robot. However, the big problem is to find the components. I mean, if you want to create big robot, the normal size robot, you can find very easily the actuators, the sensors, the mechanical parts. However, if the robot is very small, most of the time you cannot find very small actuators, and most of the time you have to design by yourself those actuators. Here you can see an example. So as you can see some examples here, this is a satellite. As you can see, the size is very, very small, and it's equipped with inertia wheels here to control the orientation of the satellite, and other examples. I will show you a short video.
We take a look at the top 10 most amazing and real micro-robots in production today. At number 10, the Arius drone. About the same size as a quarter, this amazing quadcopter can fly 7 minutes, 2 automatic flips, and has 6-axis gyro stabilization. It flies on the common 2.4 gigahertz range, and the drone fits right inside the size to recharge. On top of that, it's only $35 from the Axis Drones website. That's number 9, Robobee. For over a decade, Harvard University has been working on
80 milligrams
robots, including Robobee. Although the current version still has a
wings. And as you can see how it can move. And this wire, it brings the energy to the actuators. And its size compared to the 1 cent coin. This is an ant.
Piezo actuator legs and jaw bring this marvel to life. The ants use a 3D stereo camera for gripping objects and an optical sensor for moving. Multiple ants can work together and be used to complete complex tasks through networking. The ants are powered by a 3D electrical board.
Here a cooperation task where the 3 ants are cooperating to move.
Number 7, the Water Strider bot. Many robotic versions have
Water Strider, as you can see, it can stay
but just
on the
recently,
surface of
University
water.
has built a strider which can jump 6 inches off the surface of water and stay afloat. It weighs only 68 milligrams and maximizes surface tension
60 milligrams
its real-life counterparts. And number 6, Micro
This one is
built by
very
Stanford
amazing.
University.
Look to the payload that this robot can move, and you will be surprised.
Times its own weight. It uses micro-cohesive
This is the
pairs
basic
so that it
principle.
can pull objects up walls.
And
That's
look
pretty
here,
impressive.
he will
considering
be
that's kind of
able
like a
to
human
move
pulling
on this
200
payload.
tons. One day, powerful
It's
working
really
trucks can find
amazing.
jobs lifting heavy loads in factories or even
Very heavy
construction sites.
payloads.
At number 5, SRI bots. Controlled through magnetic fields, microbots can go up to 35 centimeters a
This
second and
it
can
uses
climb up walls. Large
electromagnetic field,
complex
and
objects
it
such
can
as
move, as you can see, very, very high speed
electronics
motion.
can even be used for
It can avoid obstacles,
And number 4,
and it
organic
can move from one
robots.
point to
Created by
another.
MIT, this bot self-assembles through a heating process, and then it can run, carry objects, and even swim. Even though the bot has to be remotely controlled by magnetic fields, it'll likely be automated in the future. The bots will likely be used for inspection in small areas such as pipelines or even machinery. And number 3, starfish bots.
Starfish,
These really cool bots
the
can be less
size
than a
is
millimeter
extremely
across
small,
and are used for
1 by 1
biopsies.
millimeter.
The starfish can respond through variations in temperature, pH, and even enzyme levels. Groups of starfish can be used for screening, and successful trials have already been conducted for detecting cancers. And number 2, microscallops. Being just a little bit bigger than a strand of hair, these microbots can move through body fluids and have the potential to deliver medicines and even repair damaged
inside the
cells.
body, human
The
body,
shell operates similar to a real-life
medicines.
lamp. It moves by opening and contracting. It's controlled by an external magnetic field. Robotic scallops are likely to be used for research and help advance nanobot delivery technologies. That's number 1, micromotor-powered nanobots built by the University of California. Propelled by gas bubbles and only being a few micrometers long, these bots have already delivered a nanoparticle compound in a light house without side effects.
The idea
Being
is
the
to
first
put it
self-propelled
inside the human
microbot, it is a
body.
huge technological.
Now there is another very important field of robotics, and it's very, very interesting nowadays because when we start the robotics by the mid of the 50s, beginning of the 60s, most of the robots, they were rigid. Well, so we construct the robot based on rigid materials. Nowadays, we are moving to soft robotics, so we try to construct the robot using soft materials. Let me show you a short video to understand.
So a soft robot is a robot that uses fabrics or soft materials like silicone and elastomers to make up the robot's structure. The soft robots are very much biologically inspired or mimic biological systems.
And look,
The ocean has a large abundance of soft creatures, yet they can do amazing, amazing things and solve incredibly challenging problems. So when you look at a soft robot, what you see is something that was inspired by nature, by the animals around us,
Here, undulating
by
the
ourselves
beams,
even. Our muscles, for instance, are
robotic
composed of
hands,
soft fibers.
grasping objects, and so on. Now swarm robotics, so the idea sometimes one robot itself is not enough. I give you an example. Imagine that you have an air crash investigation, that you are looking for black boxes and you want to cover a very huge area. So only one underwater vehicle is not enough. So the idea is to deploy a certain number of underwater vehicles to do the coordination of the motion and until you find the black boxes. And we can be inspired from animals, and here let me show you a short video to lesson this concept of swarm. We call it swarm robots. Some of the time they are heterogeneous and sometimes they are none. Here you construct certain animals like birds, ants.
But sometimes patterns emerge, like a flock of birds in flight.
Coordination.
How does a group of animals, or cells for that matter, work together in an organized way when no one's in charge? Like termites building skyscrapers out of mud, or fish schooling to avoid predators. It's called emergent behavior, order emerging from chaos. And you don't just see it in nature. Enter the Kilowatt, a robot the size of a quarter, developed by engineers at Harvard. What's so interesting about kilowatts is that individually they're pretty tough. They're designed to be simple. A single kilowatt can do maybe 3 things: respond to light, measure a distance, sense the presence of other robots. But these are swarm robots. They work together. The kilowatts can organize themselves into shapes, sort of like how cells form into an organ in your body. Here's how it works. The kilowatts are programmed all at once, as a group, using infrared light. Each kilowattt gets the same set of instructions as the next. With just a few lines of programming, the kilowatts together can act out complex natural processes. For example, how do a group of identical cells in an embryo develop into different parts of the body? In nature, this is a fairly mysterious process, but with kilowatts, you can recreate it. See here how the kilowatts start and then start randomly blinking either red or green? Their instructions are really simple. Respond to your neighbors, match their color. But just with that simple programming, they begin to differentiate themselves into red and green sections of the group, a lot like cells differentiating themselves in an embryo. For here, they're dispersing based on the way gas bubbles spread out to fill a volume. Here, a swarm of fireflies that start off blinking randomly and eventually begin to flash in unison.
Nice. Another field of robotics is marine robotics. And for marine robotics, I will show you a short video how we deploy an underwater vehicle and what are the main steps to do a mission. So if you have an autonomous underwater vehicle and you want to deploy it, first of all you have to decide about the mission, what you want to do exactly. So the mission was designed here in the computer, and then it will be uploaded on the underwater vehicle. And this is an autonomous underwater vehicle. We have different kinds of underwater vehicles. In one lecture, I will detail all those aspects, but here I just show you a demonstration. So once the vehicle here is on servers, you can upload here, you can communicate using radio signals, for instance, because it's on the surface. You can use the satellite also to communicate with the underwater vehicle because it is on the surface. However, when it goes down, all those signals, they will not work. You cannot use radio signals, you cannot use satellite, you cannot use GPS. Only acoustic signals, they work underwater. So once the mission is getting started here, the robot has to dive. And this is an underactuated underwater vehicle. It has a propeller here, and it dives in this way. So it has this spiral motion going down until it reaches the desired depth, and at the desired depth, it has a specific task to do. Depending on the task, he should communicate with the boat, as you can see here, using mainly acoustic signals. They perform very well underwater, and they can be used. Those signals, they are used by animals. Here during the mission, it depends on the sensors that you have on board your underwater vehicle. So we try to exploit those sensors to do some specific tasks underwater, like 3D reconstruction, like the detection, the pipeline inspection. You can use DVL, you can use inertial measurement unit, IMUs, and different kind of sensors. And this is the navigation using the DVL. And with the DVL, you can measure the speed of the motion of this underwater vehicle. Then you can use a side scan here using the sonars. The sonar can be used here for side scan, as you can see, for archaeology applications, for instance, 3D reconstruction. And here, as you can see on the left, it's the results of the image that you can obtain using a sonar. You can see the seafloor reconstructed here. You can take also pictures, you can take videos, you can see here the different results that they obtain. This is the video recording. You can take pictures and videos during the mission. And everything is stored inside the vehicle. So there is a memory inside the vehicle where all this data is in this memory. And once the mission is finished, you have to get the data. However, this kind of vehicles, the drawback is the energy is called autonomy, because actually you can make missions just a few hours, 6 up to 8 hours of a mission. So this is the big problem. The second problem, they are very, very expensive, and if they get stuck somewhere and you lose the robot, you lose 100,000 euros, for instance. The price is very, very high. So once we finish the mission, you take all the measurements. So the idea is to go back to the surface and to get this memory, to get all the data. And this is another sensor. It's the echo sounder, multi-beam. There is mono-beam and multi-beam echo sounder, and you can do the 3D reconstruction of the seafloor, for instance, as an application. So once the mission is finished, now the robot has to go up to the surface, and the same way it will follow this spiral motion until it gets to the surface. Why it does not go vertically like that? Because it's underactuated. This is why it moves like that. However, if you have an ROV, you can move in a vertical way. Once you reach the surface here, you can communicate again with the vehicle, and you can localize the position of the vehicle, and then you can get the vehicle back. Here, so you recover the vehicle because you can communicate with the vehicle since it's on the surface, and you can use the GPS to localize it. Once you get it, you have to get the data that you recorded during the mission. And then you have to recharge the batteries, put a new memory inside the vehicle, and you can start the next mission. Nice. Now medical robotics, as you know, robots are very well used nowadays for medical robotics, like for surgery. Nowadays we use manipulators, and one of them is this system called the Da Vinci. Let me show you a short video to understand how it works, and pay attention. This system has been designed to help the surgeon, not to replace the surgeon. Let's see how it works.
The Da Vinci surgical system is the most advanced platform for minimally invasive surgery available in the world today. The integration of high-resolution 3D vision, wristed instruments, and intuitive motion control enables the Da Vinci surgeon to transcend the limitations of conventional surgical technologies. 3 network components comprise the Da Vinci surgical system: an ergonomic surgeon's console, a patient-side cart with 4 interactive robotic arms,
as you can see, the arms,
and a high-definition 3D vision system.
3D vision system.
Seated at the console, the Da Vinci surgeon views a remarkably clear 3D image of the surgical field. The system scales, filters, and translates the movements of the surgeon's hands on the master controllers to 4 interactive robotic arms on the patient cart. The precisely controlled micro-movements of the Da Vinci instruments are enabled by the computer processors of the system. These dedicated processors perform millions of safety checks over the course of a procedure for enhanced surgical precision and control. Da Vinci EndoWrist instruments are designed with a unique wristed architecture that provides 7 degrees of freedom for a range of motion greater than even the human wrist. This proprietary design enables surgical maneuvers impossible with conventional laparoscopic tools. The system requires that every surgical maneuver is under the direct control of the surgeon. Redundant safety checks prevent autonomous movement of the instruments or the robotic arms. The Da Vinci S surgical system moves surgery forward with a new level of technical capability that enables minimally invasive surgery in complex procedures as never before.
Nice. Now, service robotics. Also, as I told you from the beginning, we have more and more robots in our society, like to help elderly people, like to prepare food, like to receive people, to communicate with people, to serve the human, and so on and so on. Let me show you a short video of a real application where we can use those robots to help elderly people at home. And this application is coming from a research project in Greece.
His name is Zacharias. He's the prototype of a robot designed to improve the independence and quality of life of elderly people who, like Ageliki Kokutsi, live alone in their homes.
¿Qué punto es esto posible?
Ageliki is 68 years old, and she lives alone in her home in Patras in western Greece. She suffers from mild arthritis, but otherwise her health is fine. And she's now volunteering for an EU-funded research project she hopes will help make a difference to elderly people like her.
The team of scientists has informed me that the robot will record my daily movements to prevent any falls or diseases.
The robot measures elderly people's walking speeds and movement patterns, and is currently being tested to see whether it can operate by itself. Any unusual data it gathers is automatically sent to a person's family or their doctor. To do this, Zacharias is equipped with sophisticated cameras.
It has a 2D laser sensor that it uses to create a map of the environment around so the robot can locate itself. It also has 2 cameras, a front camera that is also a 3D sensor and helps to study who uses movements, and a rear camera that we use to detect the elderly person when he or she is following the robot.
Nice. Now, assistive robotics. So for assistive robotics, I will show you a short video. It's the field of exoskeletons. Also for several applications, it can be for elderly people, for disabled people, for industrial applications, and for military applications. And I will show you a short video where you will see all those exoskeletons, as you can see from this.
Our skin performs a lot of important jobs, like containing our organs and picking up environmental sensations. Sometimes, though, the body is better served by a hardier exterior. Here are 10 extraordinary exoskeletons. Number 10, the shipyard workers' helper. South Korea's Daewoo Shipbuilding and Engineering tested out a set not long ago designed to help laborers maneuver heavier loads. Those wearing them were able to haul big pieces of metal in large pipes like they were fluffy pillows. Number 9, Fortis. There are countless jobs that would be made easier if everything weighed 36 pounds less. Lockheed Martin realized that and made an exoskeleton that transfers that amount of weight to the ground, diminishing human muscle fatigue. Number 8, Exos 2. There are exoskeletons and there are military-grade exoskeletons. The Exos 2 is the latter, and it provides the ability to repeatedly lift hundreds of pounds and punch through 3-inch thick wood. Further, these things can be done gracefully thanks to a sophisticated hydraulic system. Number 7, MaxFast. If a person is aiming a gun at someone, chances are they're in a pretty intense situation. To counter any shot affecting arm shaking that may occur, this brace reads minute movements, stabilizes accordingly, and increases the probability of target contact. Number 6, Power loader light. Wearable contraptions that provide superhuman strength are great. So is help with lifting heavy things around the house. That's where this exoskeleton comes in. Intended for the general public, the power loader light can handle about 100 pounds, making it ideal for lugging around furniture and boxes. Number 5, mind control exoskeleton. Over 150 researchers working in project engineered a device that can be controlled by the wearer's thoughts. Their robotic suit was highlighted in the 2014 World Cup. It was worn by a paraplegic man who performed an opening ceremony kick. Number 4, Rewalk. Classified as a therapeutic device, the robotic assist provides a wide range of movement to those with spinal cord injuries. Standing, walking, and turning can all be accomplished while wearing one. So can more involved tasks like climbing up and down stairs. Number 3, Harmony. Upper body rehabilitation equipment typically only addresses the movement of one arm at a time, leaving the need for two-arm coordination unaddressed. Harmony was created to rectify that problem. As it tends to both limbs at once, it can greatly expand the range of skills recovered by those who've encountered neurological problems. Number 2, AFA. Not only do firefighters run into burning buildings and the stairs in them, they often do it while wearing 50 and 120 pounds of gear. This exoskeleton doesn't lighten the load, but it does enhance muscle performance, making necessary equipment easier to carry. Number 1, soft exosuit. Just because robotic suits are typically made from rigid materials doesn't mean they have to continue to be. Harvard's Beast Institute is working on a textile version, which would offer many of the strength-enhancing and fatigue-diminishing benefits of the bulkier sorts, but be much easier to wear, transport, and maneuver. Which exoskeleton do you think is the most extraordinary?
Nice. And the last field now, social robotics.
What is social robotics? Imagine a robot that not only brings you something, but greets you by name, responds to your mood, or teaches you to code. Social robotics is the field dedicated to designing and building robots that can interact with humans in a natural and empathetic way. Unlike an industrial robot whose goal is a physical task, a social robot's main purpose is communication and interaction. These robots are designed with features that make them more accessible and social. They use cameras and artificial intelligence algorithms to recognize facial expressions and voice tones. They can talk, answer questions, and even use gestures to simulate emotions. Additionally, they are often programmed with a unique personality to make their interaction more natural and human-like. So, where can we find social robots? Their applications are vast and focus on human well-being. For example, robots like Aibo, the robot dog from Sony, are used as companion pets in homes to reduce stress and loneliness. There are also robots like Moxie from the company Diligent Robotics that help in hospitals with logistical tasks, allowing medical staff to focus on patients. And they can even act as guides in museums or as receptionists in stores and offices, offering information in a friendly manner. In short, social robotics is the future of human-machine interaction. Its goal is to turn robots from simple tools into companions and assistants that improve our daily lives in a more personal and close way.
Nice. Let's come to the conclusion. So the idea of this first lecture, before we start talking about the control of complex robotic systems, I try to give you an overview about the status of robotics today. So we have seen that the origin of robotics started with the industrial robots. And then nowadays, as I told you, we have a lot of fields of robotics. We have seen like mobile robotics, biosphere robotics, humanoid and legs robotics, aerial vehicles, micro robotics, marine robotics, medical robotics, service robotics, assistive robotics, social robotics, and so on. So this is a general overview, just to know that all of them, they need control. Whatever the robotic system is, the first thing to keep in mind, all of them you need to design a controller. Also, most of them, they are very complex. We will see through the next lectures the complexity of control, especially in terms of control of those kind of robots, and they choose some of them that I will present in the next lectures. Some here papers if you want to read further, some links if you want to see some videos about my research activities. I have a YouTube channel. And my research papers can be downloaded here and so on. And let's stop here for this first lecture. Thank you very much for your attention.
Giving us a more up-to-date perspective robotics today. So let's go to start the question and answer section. If you have a question, please raise your hand to bring the microphone. Someone else?
Yeah, please. Go ahead.
Thank you very much for this introduction to the robotics. Quite interesting. Yeah, I have a general question about soft robotics. What is the main challenge in soft robotics nowadays? What is the main, the actuators, the battery, which ones?
Yes. There are a lot of challenges in soft robotics. One of the big problems that we may face when we study soft robotics, you know, is the model. If you have a rigid robot, it's very easy nowadays to compute a dynamic model. However, a dynamic model of a soft robot is extremely complex. Why? Because the material is soft and you use like methods of finite elements. So the complex model, the model that you compute, it should be extremely complex, you understand? Because you take a lot of points to have a precise model and it should be very complex, and once you implement this on real robot, it will not be possible to run the model in real time. This is one of the problems. One of the other problems is the actuation itself. If you have a soft robot which is like that, how you can design the actuator itself, where you have to put it and so on. The interaction of the environment and so on. So this field, it's really new, and nowadays, for instance, we started recently working in cooperation with Estonia on an underwater vehicle where it uses fins to dive underwater. And it's not using classical propellers, but fins instead of this. And one of the ideas that we are starting working on is how to use neural networks, fins, physical neural networks, to get a model of the fins of this underwater vehicle, for instance. And I have a joint PhD with Estonia right now working on this topic, how we can use neural networks to compute a model of these soft robots. Yeah, please.
Please present first and after to bring your question.
Yes, thanks for a very discriminating lecture. I'm Miguel Torres, I'm an economist for working on automation and cybernetics. And I didn't know about KUKA, this is German, right? Yeah. When I think of Boston Dynamics, it seems to me like they are like small robots with intelligence. And from what I saw of KUKA, it seems like industrial huge robots.
Exactly. That's
dumb. Is there any compatibility between size and intelligence?
No.
Or
no, there is no. You can have a strong robot which is intelligent. You can have a very small robot intelligent. The only thing is, for instance, if the robot itself is autonomous and it is small, so actually the computation time or the computation efforts or the computation hardware will be smaller. Instead, if you have a bigger robot, you can put directly a computer, like we have an underwater vehicle equipped with fins in Estonia, and inside we have a computer. However, if you design a robot of this size, you cannot put a computer inside. You have to put a small microcontroller. So in this case, you have the computation efforts, they are not the same. You understand? This is the only thing. However, otherwise, there is not a general rule saying that it's big, it's less or more intelligent. Yeah, thank you.
Someone else? Someone else? Student, take the opportunity to ask Dr. Ahmed.
Yeah, for sure. No? Yes, there is one question there.
Please, can you tell us your name and your institution before you made your question?
My name is Victoria. I'm from Simvestab. And my question is, what is the main challenge when you work with redundant systems, such as spider robotics?
Yeah. Very good question. Let me go back and let me explain. You are talking about actuation redundancy. Redundancy in actuation, that's it? Let me go back. Yes. You are talking about actuation redundancy? Oh, nice. Let me give you an example. You know this robot? It's called Quattro. And this Quattro, you know, actually it's commercialized by Adept in the US. Now the company is another bigger company called Omron that bought Adept. But the origin of this robot, it was our lab. So we make a patent. It was not me, it was my colleagues, mechanical designers. So they designed this robot called Quattro. And it's a Delta-like robot. If you know the Delta robot of Professor Clavel, it's almost the same concept. Look here, we have 4 kinematic chains. The delta robotics has 3 kinematic chains. So here what we did, we add a 4th kinematic chain, and we have a 4th motor. So we have 4 control inputs, 4 motors, and only 3 degrees of freedom. And it's redundant. And you know, we designed first this one, and we designed another one in the same lab, in our lab, based on the same concept. And one of the advantages, there is a challenge and the advantage. So the challenge is you have 4 control inputs and 3 degrees of freedom, and the question is how you can link the 4 actuators to the 3 degrees of freedom. It's not straightforward. This is the challenge. And the advantage is, you know, if you have 4 motors and you want to move in a certain direction, instead of pushing using 3 motors, you use 4 motors to push. And using this concept, you know what we did? We reached a record of maximum acceleration, 100 G. 1,000 meters per second square. It was a record of maximum acceleration in the world. I will show you more details regarding this in the lecture of control of parakinematic manipulators, where I will talk about this problem of redundancy and how we resolve it. And just to answer roughly how we can manage this challenge of redundancy in actuation, we can use the Jacobian matrix. You can use the Jacobian matrix and introduce a term based on the Jacobian matrix to manage this redundancy in actuation. So I will tell you more during the lecture of control of parameters. The control solutions. So we propose new control solutions, we make the stability analysis of the resulting closed loop system, and also we go until the real-time experiments, and this is very important, especially if you compare like the simulation world and the experiment world, you will see that there is a big gap, because simulation is much easier than experiments, and in experiments you can expect a lot of problems beyond the problems of the control itself, implementation, the hardware, the computing time, real-time constraints, and so on and so on. So all those problems, you need to deal with them if you are interested in application in real time. And this is very important. And also something which is very important is the impact. I mean, the impact of the results, if you do just simulations or you do experiments, it's not the same. So with experiments, you will have a much bigger impact of the results that you are developing. And through this summer school, I will try also to show you this impact, this importance of doing experiments and not just doing simulations or just theory. Experiments is very, very important, especially in the real world and in different operating conditions. So, the second lecture will focus on motion control of under-actuated robotic systems. And before that, I will first introduce this idea of complex robotic systems. So we named this summer school control of complex robotic systems. So what is a complex robotic system by definition? What is a complex robotic system? So first of all, we need to look for the origin of the complexity. So if you have a system, the system is complex, from where this complexity is coming, from where it may come. Here, as you can see, an example of any robotic system, and around here you can see the source of complexity. First of all, the first source of complexity, it may come from the structure of the robot itself. This structure, for instance, you can take some robots with a high number of degrees of freedom. So coordinating a high number of degrees of freedom, this is not very easy. It may come from the flexibility of the structure. We talk about soft robots, and soft robots, they are very complex in terms of modeling. So the model is very complex, and the control is very complex. And this is why it's also a source of complexity. Also, in any robotic system, and especially in articulated robotic systems, we have the problems of singularities. You know what is a singularity? So a singularity, it's one challenge that we need to take into account when we talk about control. Then we have the problem of friction. Any mechanical system, any joints, you may have a friction. And the friction itself, most of the time, what we do, we neglect the friction. We say, okay, let's neglect the friction. Why we neglect the friction? Because it's very complex to be modeled, it's very complex to be identified, and it's very complex to be compensated in the control. This is why it's a source of complexity. and also the complex design of the robotic system itself by design. So you design something which is complex. So this is the first source of complexity, which may be related to the structure of your robotic system. Another source of complexity may come from the actuation. So you have a robotic system, however the actuation itself, it can be under-actuated. It means you have less control inputs than degrees of freedom. Or it can be the inverse, over-actuated or redundantly actuated. It means it has more control inputs than degrees of freedom. And for both cases, you cannot link the control input to the degree of freedom straightforwardly. No, because you do not have the same number. So you have to think about a way how you can link the control inputs to the degrees of freedom. You have sometimes in the actuation system what we call unilateral constraints. I will explain you this problem in a robotic system which is very well known. It's called, it's a parallel robot, and they are called cable-driven parallel robots. I don't know if you have an idea about these robots. In the lecture about control of parakinematic manipulators, I will talk about this. A cable-driven parallel robot, it's a robot where you use cables, you understand? The cables to actuate, to move the moving platform. And the cables, they are not rigid, they are flexible. It means that you can apply control action just in one direction because you need to keep the cable under tension all the time. So you apply control in this direction, not in this direction. And this mathematically can be represented by a unilateral constraint. And it can be a source of complexity. And also in any robotic system or any actuator, there is a saturation. You have a motor, you have a maximum and a minimum. You cannot go beyond this maximum. If your control input needs 100 Newton meter and your motor can deliver 150 or 50 Newton meter, 50 is the maximum. You cannot go beyond this value. And this is a nonlinearity that can be considered in the actuation of the system. So this is the second source of complexity that you may have in your robotic system. Then we have here the dynamics. And as I told you, the dynamics, it's a model that represents the input-output behavior of your robotic system. And most of the time, it's a highly nonlinear. So it's a model which is highly nonlinear. It's a model with a couplet dynamics. It means that if you apply a control input on one actuator, you affect not just 1 degree of freedom, maybe 2-3 degrees of freedom. There is a coupling between degrees of freedom. And this is not so easy. And also, we have the problem in the dynamics. Sometimes you have time-variant parameters. It means your dynamic parameters, they are not fixed. They are time-variant, and you have to deal with this variation in the parameters. Either by saying, okay, I know that the parameter is varying, and I suppose that there is an uncertainty, and I suppose that there is a bound of this uncertainty, and under this bound, I can guarantee the performance of this system that I'm controlling. This is one way. Or you can design an adaptive controller which will estimate this parameter which is time variant. So in real time you estimate this parameter and you can compensate it in the controller. So this is the third source of complexity in any robotic system. And then we have the next one, the fourth one, it's the interaction with the environment. Most of the robots, so they will behave in an environment. And most of the time there is an interaction between this robotic system and the environment. And this interaction, it's not so easy, and you have to take it into account when you design controllers, because you will want to do a task, and this interaction may bring maybe external disturbances. This interaction may be concerning the external disturbances, may be concerning the known environment. So you are evolving in an environment, but you don't know a priori this environment. It's unknown, and this is a source of uncertainty in the environment itself. And also, time-varying operating conditions can be considered in this interaction between your robotic system and the environment. And the last source of complexity in any robotic system, it may come from the real-time experiments. You want to do real-time experiments, so in this case you have to consider the most simple thing is to consider the real-time constraints, like the sample time. You know, sometimes we designed very nice controllers based on mathematical model, and when we tried to implement them, it was not possible. You know why? Because the computing time, it goes beyond the limit of the sample time. We had robotic system, this robot that I told you this morning that we reach 100 G of maximum acceleration, you know it has a complex nonlinear dynamics over actuation, redundancy in actuation, and the sample time is equal 0.1 milliseconds. So in 0.1 milliseconds, you have to get the measurement to compute the reference trajectories, to compute the tracking errors in position and speed, to compute the control input, the control torque in the four molders, and to send this to the molders in a time, all this in a time less than or equal 0.1 milliseconds. We tried to implement a computed torque that you know maybe, which is a model-based controller, and it was impossible to do this in real time because the computing time was beyond the sample time of 0.1 milliseconds. So this is the last source of complexity in a robotic system. So when you are interested in developing controllers, and especially you want to do experiment, you have to take care about all those sources of complexity in your control design. And this is why we are here to learn about those complex robotic systems. Nice. What I'm doing in my research activities, it's here in the middle. So I'm interested in control of complex robotic systems. And here around you can see the applications I'm working on. So the first topic, it concerns the control of under-actuated robotic systems. And this is the topic of this lecture. Then we have the third lecture, it will be control of parakinematic manipulators. They are very complex robotic systems also. And here we can find a lot of problems of singularities, a lot of problems highly nonlinear dynamics, a lot of problems of time-varying parameters, and a lot of problems of singularities. So, and over-actuation also. So this is why they are very complex. And this is the lecture number 3. Then lecture number 4, we will talk about control of underwater vehicles, and especially conventional propeller-actuated underwater vehicles and bio-inspired underwater vehicles. And for bio-inspired underwater vehicles, these parts, they are the fins that are used to move underwater, and they are flexible. So we use soft robotics tools to compute the dynamic model and also the control. So this is the 4th lecture. The 5th lecture, I will talk about control of humanoid robots for walking. If I have time, I will show you a recent work that we did also in cooperation with Estonia on the control of this quadruped robot. But in a specific, very challenging task. I will tell you more about this in the 5th lecture. And in the 6th lecture, the last one, it will be on control of exoskeletons. And exoskeletons, they are very complex robotic systems also due to a lot of problems. The dynamic parameters that we don't know perfectly, the interaction between the exoskeleton and the human, the control saturation of the actuators itself, the dynamic stability of the walking, and so on and so on. So all those systems that you can see here, they are complex, and through all the lectures we learn about all of them. So today, for this 2nd lecture, let's talk about the control of under-actuated robotic systems. And let's show you a short video, just to start, I mean, to situate this problem of control of under-actuated robotic systems. As you can see, this is a bicycle. And the bicycle itself, so it has different control inputs here. You control the motion of the wheels, but however you have here an inertia wheel in the middle. And this inertia wheel, it was used to control the motion in the lateral plane and to stabilize the motion of this bicycle. And if you look to the dynamics of the bicycle itself and the interaction with the ground and the dynamic model, so it is an under-actuated robotic system. And the question is, if you have any robotic system with a certain number of degrees of freedom, with a certain number of controlling push or actuators which are less than the degrees of freedom, how we can resolve the problem of control? Because it's not straightforward, because it's very difficult because of a lot of things. And let me explain you more through this lecture. So this is the outline, an introduction, then the context and problem formulation, the control problem formulation. Our experimental platform, I will show you one simple experimental platform that has been used for validation of all the control schemes that we developed for those kind of systems. It was in the lab, it was an academic system, which is representing an under-actuated robotic system. Then I will try to show you solutions about two problems. So the first problem is the problem of stabilization. Stabilization, you want to bring the state of the system around zero, starting from something different from zero, and you want to bring everything there. However, pay attention, it's not straightforward, as I told you, because you will have the problem of zero dynamics or internal dynamics, because this internal dynamics is unstable and the system is not minimum phase, and it's not very easy to find the control solution. So we will talk about the control problem formulation, the proposed control solutions, and some real-time experimental results to show you what we did. Then the second problem, we will be interested in the tracking of some reference trajectories. Here, the idea is not to perfectly do the tracking of the reference trajectories. However, we want to do the limit cycle generation. The cycle, limit cycle is a closed trajectory, it's a periodic trajectory. So we want to converge to this periodic trajectory, and we want to stabilize it. Because actually, if you design a controller and you control the actuated degrees of freedom, and to follow a predefined trajectory, there is no problem. You can follow perfectly trajectories. However, what happened on the zero dynamics of the system or the internal dynamics, it will diverge. If you don't do anything else, it will diverge and you cannot generate a stable limit cycle. So we are here interested in generating a stable limit cycle on both actuated and non-actuated degrees of freedom. And if you can tell me what's the interest of this limit cycle? Look at the human, when we walk, this is the limit cycle. If you look at the trajectories of the legs, of the joints, and plot trajectories, you see it's a limit cycle. It's a periodic motion. So one of the applications can be this, for instance. So we will talk also about the control problem formulation, the proposed control solutions, and some simulation and real-time experimental results. And then I will conclude by the end. So let's get started from the beginning. And the first question that we may ask is, what is an under-actuated robotic system? Let me show you short videos to understand, to see this problem. And the first one, it's like the same problem of the bicycle. It's the cube. So it's a cube. Actually, it's like a satellite. In a satellite, you have 3 inertial wheels. And using the 3 inertial wheels here, by rotation of the 3 inertial wheels, you can control the orientation of this cube. And you can move the cube, you can put it on the corner, you can stabilize it in the vertical position, as you can see here, using the 3 inertial wheels. And this is an under-actuated robotic system. So this is the first example. Second example, now to situate the context, let's start with the definition. What is an under-actuated robotic system? So in robotic, we can distinguish 3 kinds of robots. So the first case, as an example here, I give you a robotic arm with 6 degrees of freedom. So 6 joints here, as you can see. And the robot is equipped with 6 motors. So it means the number of degrees of freedom is equal to the number of motors or control inputs. It means that this robotic system is fully actuated. This is the first example. Then we have a second example. Imagine that you have a robotic arm like that, and instead of you have 2 joints here, one joint, like it's like a human arm, 1 joint and 1 joint. And suppose that you will not put 2 motors, just 1, and you put the motor in the middle here. Is it possible to control using one motor this passive joint and this active joint? Using one motor, we want to control 2 degrees of freedom. This is the question. And we have 2 degrees of freedom in motion and 1 actuator, and this is under-actuated. However, in robotics also we can find the inverse of this problem. Sometimes you have more motors than degrees of freedom. And also we have the same problem, how you can coordinate those motors to control the number of degrees of freedom, and we call them over-actuated or redundantly actuated robots. So we are interested here today in this class of under-actuated mechanical systems. Let me show you some videos to understand. This is the case of the acrobot. As you know here, we want to make it the swing up. So we move from the down position to the up position and using just one motor. And the motor is situated here in this articulation. This is a passive joint. And as you can see here, we reach to the vertical position, which is an equilibrium point, and we try to stabilize the system around this position. So this is one example. And the degree of actuation, we can define it as the difference between the number of degrees of freedom minus the number of actuators. So here, 2 minus 1, so the degree of under actuation is equal to 1. For sure, if the degree of actuation is bigger, the problem is more complex. So this is one example. Let me show you another example, which is here more complex. It has 4 degrees of freedom and 1 actuator. So we have here the card, and it has 1, 2, 3 joints. So 3 joints and the card, so 4 degrees of freedom and 1 control input. And it's the same problem as the previous case. It's the swing up control. So we want to move from the down position to the up position, and we want to keep the robot around this vertical position stabilized. So here they compare the swing up control with the controller, and here without the control, and as you can see, the degree of instability of motion. As you can see, it's continue moving because it's highly unstable in this case. But here, if you are controlling, you stabilize quickly the system, and you move from, it's not the swing up, it's the swing down. You move from the up position to the down position. Anyway, so this is the second example. Third example, it's an aeronautics. You know, this is an airplane, and this airplane, it has a specific feature. It has propellers, and the propellers are used to push the airplane in this direction. The propellers themselves, you know, you can orient them. So you can change the orientation of the propellers such that your airplane, it can move, it can take off and land in vertical way, like that. You understand? This is what we call planar vertical off and take off and landing aircraft. And look how it works. Here you will see how it will land. It's moving like that. Then it turns the propellers in a vertical way, and now it's moving down. So the propellers are oriented downward. And then we try to control the motion or the propellers force here to go slowly until we touch the ground. So this is landing in a vertical way. This is what we call the pivotal. If you look to the dynamics of the pivotal, so in the plane, it's here. So this is the airplane. The center of gravity is here. You have X and Y, and you have the orientation angle theta here. So we have 3 degrees of freedom, and we have only 2 control inputs, which are the propellers here, U1, and U2 is the control of the angle. So 2 control inputs and 3 degrees of freedom, and it is under actuated. So this is the third example. Now, let's go back to the definition and the control challenges. So, by definition, an under-actuated robotic system, it's a system with less actuators than degrees of freedom. And now the question is that you may ask, why the system is under-actuated? So from where this under-actuation may come? So there is 2 sources of under-actuation. So the first one, it was decided in the design stage. So you design a mechanical system or robotic system, and in the design you choose to put less actuators than the degrees of freedom. Why? Because actually you want to reduce the cost. You remove 1 actuator, you reduce the cost. You remove the weight. You remove 1 actuator, you reduce the weight. You can also reduce the consumption, and so on. So for these reasons, you decide in the design stage to be under actuated. So this is the first source. Second source of under actuation. Let me explain this on a concrete example. You know satellite, how the satellites are controlled. You have seen the cube lift. It's exactly this principle which applied to control the attitude, the angles, roll and pitch, and yaw of a satellite. And inside the satellite you have 3 inertial wheels, and using the acceleration, deceleration of the inertial wheels, you can control the attitude of the satellite. And here you have 3 degrees of freedom, 3 inertial wheels, 3 control inputs. So it's fully actuated. Suppose that you put your satellite in its orbit, and after 6 months, one of the motors is broken. What happened? So you move from the fully actuated to an under actuated. Here you didn't decide about the under actuation, but the system became under actuated because of the faulty of one of the motors. And this is the second source of under actuation. So it's after the deficiency of 1 actuator or more, the system was fully actuated and it becomes under actuated. What is the consequence? So in under actuation, there is a nonlinear coupling between the actuated and non-actuated or unactuated degrees of freedom. That's the first thing that you have to take into account. And the second thing, you have a part of the degrees of freedom that are actuated and the part is not actuated. If you control one part, the other one, it's what we call the internal dynamics. And if this internal dynamics is unstable, it means your system is non-minimum phase. This is a nonlinear, non-minimum phase system. And in terms of control, if you don't do anything, you just can take care about the actuated part, the non-actuated one will diverge and it's unstable and it does not work, your controller. And this is the big challenge. Now, let's go through the equations to understand how this works. And let's see how the dynamic model can be seen. So if you learn about robotic manipulators, a dynamic model can be written like that. So you have the different terms. You have the inertia term here, the matrix M, and the acceleration Q double dot. Q is the generalized coordinated vector. Then we have the Coriolis term here, we have the gravity term here, and we have here the control input U multiplied by this matrix R. Sometimes we can add a term representing the friction. Okay? And also pay attention, this dynamic model represents a free environment. It means that your end effector is not in interaction with the environment. Because if the end effector of your manipulator is in interaction with the environment, there is a contact. In this case, you have to add here another term which is equal the transpose of the Jacobian matrix multiplied by lambda. And this represents the interaction forces between the end effector and the environment. So this is the dynamic model. The specificity for under-actuated robotic systems is here the presence of this matrix R. And this matrix R will distribute the control inputs on the degrees of freedom. It means that if one degree of freedom is not actuated, you will have 0. You will have tau 1, tau 2, tau 3, 0, for instance. Understand? These kind of things. Let's see. So this is the general model. So in this case, if your system is under-actuated, you can rewrite it like that. It means that you will distinguish the actuated part from the unactuated part. And in this case, as you can see, QA is the actuated part and QNA is the non-actuated part. So we split the dynamic model in two parts. Here we have the inertia matrix, the Coriolis, the gravity, and the control input. And remember what I told you, here the presence of 0. It means that there is no control input that will act on the second degree of freedom. So you have a system with 2 degrees of freedom. The first one is actuated by tau, and the second one, there is no control input. So you cannot act, you cannot change this degree of freedom directly. There is no direct actuation that will affect this degree of freedom. And this is the challenge. So if you are doing a control, you design tau here, you can control this first part, but what happened on the second part? And this second part, this is what I told you at the beginning, this is what we call the internal dynamics, which is most of the time unstable and the system is non-minimum phase. And if you don't do anything else more than designing a classical controller here, it does not work because the internal dynamics will be unstable. That's it here, it's just we define the degree of under-actuation as I told you, n minus m, and tau is the control, the vector of the control inputs. So in the control problem formulation, if you take this dynamic model of this under-actuated system and you try to find a control input tau here, so you can arrive to either this situation or this situation. It means that you choose tau such that you will linearize 1 degree of freedom. You cannot linearize 2 because you have 1 control input. Either you linearize with the actuated part or with the not actuated part. And in this case, the remaining part is represented by this equation or this equation. So in this case, you want to design a controller. Here you have the linearized part, you linearized with the actuated part, and this is the internal dynamics. And this is, it's the inverse, so you linearize with the non-actuated part, and the actuated part remains as internal dynamics. So pay attention, it does not mean that 1 degree of freedom is actuated, I can linearize only with respect to this. No, you can use this control input to control the one which is not actuated. It's possible, and this is what we can see here. And here the new control input, it's big that you can design with any feedback controller. You can put PID, you can state feedback, you can put optimal control and so on. But as I told you, the big problem is the nonlinear dynamics, which is unstable. Let's take the example of the pivotal that I show you, the video. So this is the pivotal. So if we look to the pivotal, so this is the picture, and this is the dynamic model. And the dynamic model in the plane, so it has x, y, and theta. So x double dot equal to this. This is the first equation. This is the second equation. This is the third equation. However, if you look to the control inputs, you have like, look here, U1, U2, U2, U2. What we remark? We have two control inputs, 3 degrees of freedom. And remember what I told you, there is a coupling between degrees of freedom. It means, look, U2, it acts here, and here. U2 is everywhere. You understand? And U1 here, and U1 here and here. So there is a coupling between the degrees of freedom. And we want to look to the dynamics, what happens if we do a nonlinear feedback linearization. So this is the representation of the dynamic of the kinematics of the airplane. So we have U1, U2 and 3 degrees of freedom, and then you have U1, U2 equal to this. So if we want to find a nonlinear feedback such that you will do exact feedback linearization, you can do just linearization of 2 degrees of freedom. Look here, I choose U1, U2. This is an expression, okay, and based on this nonlinear system, if I replace this nonlinear feedback, I get to this. What represents this? It represents here a double integrator for x and y. So I linearized 2 degrees of freedom, x and y. However, for theta, the angle theta, it's still nonlinear. This is the internal dynamics of the system. Now, if I apply any control input here in V1, V2 to stabilize, for instance, x and y, or track reference track G's, let's look what happened on these dynamics, these internal dynamics. Let me show you the video, and you will see what happened in this case. No, that's not working. I don't know, there is a video, but it does not work. Sorry. No, sorry. It's a video that shows you that the internal dynamics, it do something randomly like that, and it's not stable. Then, if we do something else now, we try to do linearization with respect to y and theta double dot. The same, we use the two control inputs. We can get up with these two linearized dynamics as a double integrator. However, for x double dot, it's still nonlinear and it is unstable. This is the internal dynamics. And the same also, I have a video, but I'm not sure that it works. Let's try. No. Let me try it here. Ah, nice. So it works here. Let me go back to the previous one. Show you the previous one first. Look here what happened. Look on theta. So we can control 2 degrees of freedom, but the third one, it's unstable. So this is the first illustration. As you can see what happened. Look here. So this is the previous equations that I show you. And now if you do linearization with respect to y and theta, you will see what happened on x. Here you go to infinity, so it's also the same problem. So this is the big problem in terms of control, as I told you, and if you apply straightforwardly feedback linearization, what happened on the zero dynamics? And the important question is, how can we stabilize these dynamics? How we can proceed to stabilize these dynamics? For sure, the other linearized dynamics are stabilized, but how to stabilize the zero dynamics or the internal dynamics of the system? And this is the big question. Before presenting some solutions, let me show you some examples. Examples of under-actuated robotic system, we can find the case of the Acrobot and Pongibot. You know, it's a planar manipulator with 2 degrees of freedom, and you choose where you put the actuator. you put it here or here, but you have just one. If you put it here, you have the case of the acrobot. If you put it here, you are in the case of the bungee. And for both, it's under actuated. The case of the pivotal that I show you, you have seen the demonstration how the internal dynamics is unstable. If you take the case of flexible arms, here you have two joints, a flexible arm. So it has two control inputs, this smaller, and you have the links here. But the links, they are flexible. It means when you compute the dynamic model, it's not enough to consider just 1 degree of freedom here and 1 degree of freedom here. Since they are flexible, you have to take more degrees of freedom here and here. So you will have the same control inputs too. However, the number of degrees of freedom, since you take here maybe 2 or 3 points, you will have more degrees of freedom and with only 2 control inputs. And this is under actuated. We have the case of some walking robots like this one, Rabbit, and you have a punctual contact between the legs and the ground. And if you look to the dynamics of this, it is also under actuated. It has like 5 degrees of freedom and only 4 control inputs. It's the motors that you can see here in red. 1, 2, and the other side 1, 2. So 4 motors, 5 degrees of freedom. This is when it is in contact with the ground through one leg. If it is flying, it's much more complex, 7 degrees of freedom and 4 control inputs. Anyway, for underwater vehicles, we can find a lot of examples, especially for surface vehicles and underwater vehicles. This surface vehicle, so it has X, Y, and angle, the yaw angle, and it has only 2 control inputs. You can control the orientation and the speed, and that's all. So 2 control inputs and 3 degrees of freedom, and it is also under actuated. And this is just some examples. We can find a lot of examples in robotics, mainly of under actuated systems. Now let's focus on the example of under actuated systems that use the gyro stabilizer. What is the gyro stabilizer? This is what I explained to you before. The case of satellite, you put an inertia wheel, and the inertia wheel is used to stabilize the system. An actuation is an inertia wheel. And here is the case of the basic simple inertia wheel inverted pendulum. It means that you have a pivot here, it's a joint without any control input, and second joint here with this inertia wheel actuated. So there is a control input here and there is no control input here. 2 degrees of freedom and 1 control input, and it is under actuated with under actuation degree equal to 1. Now if you look to the idea of using a gyro stabilizer of this inertia wheel, the idea itself, it's very old, it's not new. Because look to this picture, this is a vehicle, it was designed around 1914. And it's stabilized using an inertia wheel. So it's a very old idea. You can have another example here. This is a tramway, and it has 2 inertia wheels inside, and here it has just 2 wheels, okay? And it is under actuated also, 1903. And you have this prototype, it was not commercialized, from Ford, and it is like 2 wheels car, and inside you have a gyro stabilizer, an inertia wheel to stabilize the motion in this lateral plane. And you have I will show you a short video about this vehicle. It has 2 wheels also, and it has the gyro stabilizer, and inside 2 inertia wheels are used to stabilize the motion of this vehicle. This is the demonstration of this vehicle. You will see how it works. So it's like a motorcycle, it has 2 wheels, and it has, the inertia wheels are in the bottom part, and they are used to stabilize the motion of the vehicle.
This patented gyroscope stability system, known as the Advanced Electric Vehicle, allows the C1 to remain in a vertical position at all times, making it the motorcycle that never falls. The C1 is a prototype that constitutes an evolution of urban mobility, blending efficiency and safety in a vehicle that, in certain aspects, is close to automotive concepts. While it moves on 2 wheels, the occupants are protected by a closed structure and travel on conventional seats, not the usual motorcycle accuracy. The powerful stability system, patented by Lit Motors, utilizes moment-control gyroscopes that produce thousands of foot-pounds of torque, allowing the vehicle to gracefully enter tight corners and stay upright when faced with challenging conditions. Designed for maximum efficiency and high-speed travel, the C1's exterior is simple and accessible, offering the comfort of a compact ride and the excitement of traveling at high speeds. Its expansive glass, subtle curves, and softened volumes make it desirable and highly functional. Powered by two 54-horsepower electric motors, the C1 is capable of reaching a top speed of 190 kilometers per hour, with an acceleration from 0 to 100 kilometers per hour in 6 seconds and a range of 240 kilometers on a single charge. It's complete.
This is the inertial wheels I'm talking about.
And protection of a modern car, complemented by a sound system,
Through the
luxurious
acceleration,
and climate
we can
control.
stabilize
and stopping the stand facilitates the vehicle's upright
external
position,
disturbance,
while occupants safety
and the inertial wheels, or we call them also reaction wheels.
Seat belts, and multiple airbags. All critical devices and protection systems are duplicated and even tripled to ensure at least one is operational in the event of a main failure. With dimensions of 1.4 meters in length and 1 meter in height to shelter its occupants, the C1 is a peculiar hybrid vehicle between a car and a motorcycle that uses electric propulsion and batteries for extended range. Initially, Lit Motors plans to produce the first 10,000 units of this curious vehicle.
So they are rotating, and you change also the orientation of them, such that you can compensate for the effects in the lateral
with a suggested retail price of $32,000 and an estimated delivery date of 2026. The Lit.
Nice. Other examples you can find, academic examples like this one. You can find the Cubelin with 3 degrees of freedom, 3 inertial wheels. They are used gyroscopes also for stabilization of AUVs, boats like that, vehicles. We use inertial wheels. For air applications also you can use inertial wheels. They are used for satellite and so on. So a lot of applications. I will show you here one example to produce a satellite stabilization of the orientation of the satellite. As you can see here, it's based on inertial wheels, and we are controlling here the orientation of the 3 degrees of freedom of the attitude of the satellite. Here, as you can see, it's a ball, and we can change the 3 degrees of freedom, rod, pitch, and yaw. And here we are controlling these 3 degrees of freedom based on the control of the acceleration, deceleration of the inertial wheels of this satellite. So if you want to work on satellite stabilization on Earth, you can design a system like that, and you can use the inertial wheels to stabilize the satellite. Nice. Now let me talk about one experimental platform that we have to validate our control solutions before I will introduce the control solution that we propose for the stabilization and also for the limit cycle generation. So the system itself, it's the inertial wheel inverted pendulum. So it has, as I told you before, one joint here which is passive, one joint here which is active. This is the body of the pendulum, as you can see here in yellow. This is the inertial wheel which is actuated. There is a motor here actuating this inertial wheel. And the idea is to stabilize the body of the pendulum and also the motion of the inertial wheel. So this is the idea. We want to stabilize these 2 degrees of freedom using just one motor. So if you look at the components of the system itself, the mechanical part is here. So we have the 2 passive and active joints. The inertial wheel is here. The motor is behind to actuate this. For the measurement, we have to measure the 2 degrees of freedom. For the motor actuating the inertial wheel, we can measure the angle in real time. So we have an encoder equipping the motor, and we can get the measurement. And now to measure the angle with respect to the vertical, so we put here a sensor called inclinometer, and it measures the angle with respect to the vertical. And this system itself, so it has 2 degrees of freedom, and it has 2 equilibrium points. So one equilibrium point which is stable and one equilibrium point which is unstable. And it's much more difficult to control the system around or to stabilize the system around the unstable equilibrium point, I mean in the upright position, than the one that it is stable, which is the down equilibrium point. So how it works, this system? So it works based on the inertial wheel, because the control inputs, the energy is coming from the motor actuating this inertial wheel. And if you move this inertial wheel, you accelerate or decelerate, you will generate a torque here on the pivot, on this non-actuated degree of freedom. So if you look here on this pivot, the idea is that we have two torques. So the first torque, it's this one, which is due to the gravity. You have here a gravity, which is in this direction, and this force will generate this moment. If you accelerate or decelerate in the inertial wheel, you will generate another torque here. And the idea of stabilization is to work on this torque such that you will compensate for the gravity. If they are equal, you will stay like that. If you want to move like that, you have to choose this one smaller or this one smaller. It depends on the situation, but it's based on this that we can control this angle with respect to the vertical. So this is the idea. The experimental platform, as I told you, it represents here what the whole part, the mechanical part that I just explained is here. And this is the electronical part, and we have a computer, we have the motor driver, the power supply, and so on and so on. And here we have to design our controller. So in real-time experiments, so we design the controller and we have to implement the proposed controller in C++ language, and we have to compile and execute it in real time. And in terms of measurement, we get there just the position measurements, the two angles. And since for the system in control mainly, you need the state. You need, so the position and the speed. In this case, we take both measured positions and we compute the derivative of the speed of the positions to obtain the speeds, and then we use them in the feedback controller. Let's go back to the equations now and to see how we can design a controller for the stabilization of this underactuated system. So if we represent the dynamic model of this inertial wheel inverted pendulum, the equations rise like that. So here, as you can see, you have the first degree of freedom, θ1, which is the angle of the body of the pendulum with respect to the vertical, and the second degree of freedom is θ2. And θ2, it represents the angle of the inertial wheel. So we have two joints, θ1 and θ2, and we have one control input, which is U, which is the torque that we apply on the inertial wheel. So the dynamics writes like that, and as you can see, it's nonlinear, and then it's underactuated because you have here 0 and you have U. If we want to write this dynamics in a state space representation, a nonlinear state space, you have to compute the accelerations, you have to invert this matrix here, and you get up with these two equations, θ1 double dot, θ2 double dot, and then you can write it in the form x dot equal ff x and u as a nonlinear system, and you have just one control input and 2 degrees of freedom. And here's the definition of the two terms I and ml bar. So this is just to represent the dynamics and write it in state space representation. And now the question is how we can control, how we can find the control input U such that you can stabilize both degrees of freedom, actuated and non-actuated. And let's start with the problem of stabilization. And let me explain first the objective. The objective of any stabilization, it means like for the airplane, you want to do the stabilization of airplane, it means the airplane is somewhere like that, and you want to go back to 0. Here on this system, we suppose that we are in this initial condition, or initial state, where the state is different from the equilibrium. This is the equilibrium, and we want to go back to around equilibrium. We want to arrive to this situation. However, also we want to keep it around this equilibrium point, even if there are some external disturbances. So the idea is to stabilize and keep the system around this unstable equilibrium point. And as I told you, the system has two control inputs, two equilibrium points. So the first one is this one, so upright position, and it is unstable. Why unstable? Because look, imagine that you are here, and you push just slightly the system by 0.1 degree. So it goes down under the effect of the gravity. Why? Because this is a pivot here. There is no control input. So this is why it's unstable. In the other side, if you are in this position, if you move it like that, under the gravity, it goes back to this position. Understand? So it means that it's a stable equilibrium point. So down part this is stable, and this is unstable. And in control, we can find a lot of works concerning swing up control. And the swing up control, it's moved from the stable equilibrium point towards the unstable equilibrium point, and you stay there. This is the swing up control. Nice. what are the main solutions that we proposed? Actually, we proposed different kind of solutions to this problem. One of the first solutions that we did, I will show you the results. We make a linearization of the system around the equilibrium point, and then we designed a linear controller. And we designed a linear multi-predictive controller, and it was enough to stabilize the system. However, if you stay far away from the equilibrium point, it will not be enough. Okay? But if you stay around the equilibrium point, you are not far away. I will show you some results. Like few degrees or 3 degrees, maybe 6, 7 degrees, it's okay. You can bring the system up around the equilibrium point. So we tried like nonlinear state feedback, optimal control, predictive control, passivity-based control, sliding mode control, high-order sliding mode control, flatness-based control, and so on. And we tested the proposed solutions in different configurations. So the first configuration is the nominal case. It means that we suppose that there is no external disturbances. We don't disturb the system itself, and we want to stabilize it. The second example, or the second scenario, we try to stabilize the system and we apply punctual external disturbances. We apply force, and then we remove the force and check if the controller is able to reject this external disturbance. The third one, we try to add a persistent external disturbance. It means the disturbance is here all the time. And how we did it, you know, we fix here a small mass, attach it to the body of the pendulum. It will generate here a torque, which is present all the time, and then we have to compensate this in real time. This is what we did. And in the last scenario, we tried to combine both, the punctual external disturbance and persistent external disturbance. So the solution that we proposed, it's based on multi-predictive control. And here I will, for those who don't know multi-predictive control, I will try to explain in few words. What is multi-predictive control? So it's a control scheme based on a model. So you need to have a model. I'm not saying that you need to know mathematical model. It can be black box, it can be neural network, it can be anything. You have something that represents the input-output behavior of your system. This is needed first. And then it's a scheme that is explained here. The idea is the following. Suppose that you are here, you define here the sample times, you define what we call the prediction horizon and the control horizon. And then at each sample time, you have to do a prediction, a future prediction, based on the dynamic model or the black box model, whatever. You do a prediction, and in this prediction, you try to resolve an open loop optimization problem. There is no feedback, it's an open loop. You compute the optimal control sequence, which is here. Once it is computed, you will not apply all the sequence. You will apply just one sample, the first one. You apply the first sample, then what you have to do? You have to shift the horizons. The zero will not be here, will be here. And this is why we call it also receding horizon control, okay? So we move here and we repeat the same problem. We resolve an open loop optimization problem. We compute an optimal control sequence. We apply the first one, we move the horizon and repeat. But the question that you may ask me, we are talking about open loop. When we have to close the loop? Yes, here there is a closed loop. We solve an optimization problem which is open loop. However, when we close the loop, you know, when we apply the first sample, we get the measurement. This is the feedback. We get the measurement and we start from the new state here. The system, suppose you apply this, you arrive here, so you consider that this is the initial new state. And by taking this measurement as feedback, this is the closed loop. And you repeat the scenario. And it's a robust controller. It works for linear, non-linear, it works for stable, unstable, it works for continuous hybrid, it works for a lot of problems in controller. Now the question that you may ask, what would be the application of multi-predictive in robotics? So in robotics, we have another issue. Because robotic systems, they are mechatronic systems, or they are fast systems. So if you have to resolve an optimization problem at each sample time with a highly nonlinear dynamic model and the computing time is very small, equal to the sample time, it's a big problem. Yeah. If the model is extremely highly nonlinear and the sample time is small, you cannot apply this in real time. Once again, it's a constraint of real time that cannot be respected. And this is why nowadays there is a direction of predictive control towards the control of fast mechatronic systems or robotic systems, because it's very challenging to control them. When predictive control has been developed for the early years, it was by the 70s. So mainly the applications of modern predictive control were what? Like chemical generators or reactors, because you control the temperature, and it's increase or decrease slowly. The sample time, it can be 10 minutes. In 10 minutes, you have enough time to do the optimization, to resolve the optimization problem, to find everything. However, in mechatronic systems or robotic systems, if you have 1 millisecond of a sample time, it's not possible. Okay? And this is one of the challenges. However, the good thing is that if your model is linear, you have no constraints, the optimization problem is quadratic, you have an analytical solution. You have not to resolve an optimization problem online. You have an analytical solution as a state feedback, and you can apply it in real time. You have not to resolve an optimization problem to call a solver, you understand? And this is what we did in our case. So what we did, this is just the block diagram that explained the concept that I explained here. So as I told you, you have the plate here. This is the optimization problem. This is the optimizer. You need to define the closed function. You need to define the constraints. The good thing in modern predictive control that distinguish this controller with the other controllers, you know what it is? The constraints here. I mean, you will see when I talk about the control of parallel robots, and especially the case of cable-driven parallel robots where we have unilateral constraints on the control inputs. The only good solution for those systems is modern predictive control. Why? Because you can put the unilateral constraints here when you design your controller. From the beginning, you know that your control generated, it's all the time positive, because you need it to be positive, you understand? So this is the optimizer, and then this is the model that I told you. It can be equations, it can be black box, a neural network, whatever, okay? And then you close the loop here. This is the prediction. You can use the prediction error, the future errors, you resolve an optimization problem, you apply the first sample to the plate, and the future control moves here, and you close the loop, and you repeat this. So in our case, what we did, we tried to apply this model predictive controller, and we tried the case of linear model predictive control. So what we did is the following. We start from the dynamic model of the nonlinear system, which is underactivated, and then we try to do a linearization, not using state feedback. Pay attention, it's not an exact linearization, it's an approximation around the vertical, around the equilibrium point where you want to stabilize your system. And we did this approximation. From this nonlinear system, we get this linear system. And as you know, for those who learn control, this is a linear system. It's a continuous linear system. And model predictive control should be designed in discrete time. In this case, we did the discretization of this linear system. We obtained the discretized linear system, and then we designed the controller. But before that, we defined something else. We designed the variation of the control input here, the step on the control input, and we take it as a control input. So we just rewrite this model as like that by defining this extended state vector here. And then the design control is based on the optimization of the cost function. And the cost function is here. Most of the time, the cost function is based on two terms. The first time, it takes the tracking error. It means I want to be here, I am here, I take this error in the time, all the time. And I take the square, for instance, of this error. The tracking performance. And the second term, it will be the energy, like in optimal control. You take a quadratic term here, depending on the control input. And then you can have a compromise. Because both terms, you can add weighting functions or weighting coefficients, and if you want to give more importance to the tracking, so you increase the coefficient which is used on the tracking performance term. If you want to reduce the energy, whatever the tracking is, you can degrade the tracking, but you want to reduce the energy consumption, you can increase the term that you have here. And you can tune them to have a compromise. And finally, since the system is linear, without constraints, and the problem is quadratic, no, look, this is the solution. It's a state feedback with K. The state feedback gain represented by this. So it's like a state feedback control. This is what we did, and let me show you some of the results. So we start with the first scenario here. In the first scenario, it was the nominal case. It means that there is no external disturbances. We suppose that we are somewhere here, and this corresponds to the pendulum on one of the two edges, the right or the left. And here, as you can see, it's like 7 degrees. And we try to go from this to stabilize the system around 0. This is the angle of the pendulum. This is the speed of the angular speed of the pendulum. And here, this is the speed of the inertia wheel that is used to control the system, and this is the control input used to actuate this inertia wheel. Let me show you a video to see how it behaves, the system. Look, this is inertial condition. Look, the inertia wheel. It accelerates. It moves from this initial position until we reach the vertical position here. It's the unstable equilibrium point, and we want to stay around this equilibrium point. So this is the first scenario. As you can see here, we have slightly more friction, and look, normally in reality it will never stop. It's still rotating to the right, to the left. But since we have small friction in the joint, it stops here and it stays in the vertical position. This is very rare to have this situation because it's very unstable and it has tendency to go down. So this is the first scenario. Now a second scenario, what we tried in this case, we tried to apply a persistent disturbance. And as I told you, how we did it, we fix a mass on the body of the pendulum that generates a torque, which is present all the time, and then we'll see how we compensate for this torque. Nice, if we look to the evolution of the states of the system, this is theta 1, the angle of the pendulum. We start from the same initial condition. Look here, we oscillate. We don't converge perfectly to 0, but we are around 0. Why it's close to 0, but it's not equal to 0? Because of this external disturbance, which is present all the time. This is the speed of the pendulum angle. This is the inertia wheel. Look, here the inertia wheel, it's continually rotating to the right, to the left, to compensate for this external disturbance, and this is the control input involved. It's the tension that has been applied to the motor. Now let me show you the video to see how it works. Look here, this is the mass that generates the external disturbance. Look to the inertia wheel, all the time it's rotating. It's normal because you have this external disturbance, and to compensate it, you have to continue rotating all the time to compensate for this external disturbance. So this is the second scenario, and here it will never stop, because if you stop, you will go down. You will go away from this equilibrium point. So to stabilize the system around this equilibrium point, you have to continue rotating all the time. Next, the third scenario now, we try to apply external disturbances. We try to push the pendulum body and check if the controller is able to reject this external disturbance. Look here, we start from the initial condition. We stabilize the system here. Look here, this is the first disturbance, second, third, fourth. We apply 4 external disturbances, and as you can see, the controller is able to reject the external disturbance and brings back the trajectories around the desired value of 0 here of stabilization. The speed of the pendulum, and also here the inertia wheel, reaction wheel, we call it also the reaction wheel, because once you disturb, look here the reaction, what happened. It should accelerate to compensate for this external disturbance. And once we go back around the value, look, we go back around 0 here as acceleration of the inertia wheel. So this is the inertia wheel, and this is the control input in terms of tension applied to the pendulum, to the inertia, to the motor. So here we stabilize the system, we are around the vertical, unstable equilibrium point. Now we apply external disturbance, and look to the reaction wheel. When you apply the force, how it reacts. As you can see, it should accelerate more or decelerate more, depending on the sense of this force, we apply in which direction. And the idea is that the sensor detects that there is an error, and we try to compensate for this error using the reaction wheel in this case. And the last scenario, here we try to combine both disturbances. It means we have the persistent disturbance and we apply external disturbance also. The different curves, we start from around 10 9-10 degrees, we converge around 0 here, oscillating. We see the effects of the different punctual disturbances, the speed of the inertia wheel. As you can see, it's slightly noisy. We know why? Because we take the measurement as it is, and we compute the time derivative, numerical derivative, that amplify the effect of the noise, as you can see here. And this is the speed of the inertia wheel, as you can see, and how it reacts to each external disturbance. And this is the control input, and let me show you the video to see what happened. So the same as here, you have the mass, the inertia wheel is rotating, and we try to apply an external disturbance here. And as you can see, the reaction will try to change the motion based on this external disturbance in the objective of going back around the stable equilibrium. So this was done using a model predictive controller that I explained to you before. Nice. So this is for the problem of stabilization. Also, we try something else. We try an adaptive super twisting algorithm, a high-order sliding mode controller, also for the problem of stabilization. I will not detail all the equations, but I will present you the block diagram of the proposed controller. This is the system. The controller itself, it's here, super twisting control. We have the adaptation law that here that adapt the gains K1, K2 here, and then here tau that is sent to the control system. We have the feedback. We have a change of the coordinates here, the desired trajectories that are computed, and the sliding surfaces is computed here, and we fed this to the super twisting controller. And here the different equations that are known for the super twisting control, and here the adaptation algorithm that we used here to adapt in real time the gains of the controller. Let me show you, the results. Here we compare different controllers, a classical sliding mode control, the adaptive sliding mode control, adaptive super twisting control, and the super twisting control, and also the rise feedback control. So we compared like 5 controllers here, and as you can see, the behavior is all the same. We start from the same initial condition, but as you can see, the behavior of the different controllers are not the same. And the one that we proposed is an adaptive super twisting, is the black curve, as you can see here in the middle, which is the best one here. Here it has a big overshoot maybe, not the others also, but then the performance is the best. And also here, this is the phase portrait to see the convergence to the equilibrium point here. We start from here and we converge here. This is the speed of the inertia wheel, and this is the control input. Now, the last part, it concerns the stabilization. So limit cycle generation. So we want to generate stable limit cycles, and on both actuated and non-actuated degrees of freedom. Let me explain first the purpose, the objective, what we want to do. So assume that the system is in a certain initial condition here, and we want to find the control input to bring to bring X, the state of the system, and maintain it around a periodic trajectory. Okay, we are somewhere, we want to bring it, and we keep it around the periodic trajectory, oscillating trajectory, while, this is the most important, the last one, while keeping the internal dynamics stable. Okay, so if you do tracking of the reference trajectories for this periodic trajectory alone, without taking care about the internal dynamics, as I told you, it's unstable, it goes away, and it does not work. So we have to find a solution to stabilize also the internal dynamics while following the trajectories of this oscillatory motion. So the idea is to go from this initial condition to this situation where we have a periodic motion here, periodic. So we oscillate from to the right and the left, something like that, which is periodic, while keeping the internal dynamics stable. So this is the objective. So we propose different solutions. Let me show you the first one. And the first one, it's based on the nonlinear feedback linearization. And as I told you from the beginning, since the system is underactuated, you cannot do full state feedback linearization because you have 2 states, you have 2 degrees of freedom, and 1 control input. So what we can do, you can do a partial feedback linearization only. It means that you can linearize just a part of the dynamics. So this is what we did in our case. We have here a partial feedback linearization. We close the system with this. We linearize just one part of the system. Okay? And here the other part, which is the nonlinear dynamics or the internal dynamics. We consider here the reference trajectories. We trace some polynomial reference trajectories, and what we did here, we did another optimization to stabilize the internal dynamics. So we combined a state feedback controller with an optimization, an online optimization that generates the parameter P that acts on the reference trajectories to stabilize the zero dynamics. So this is the idea. And then we added something else. We designed also a disturbance estimator. We estimate the disturbances and we compensate them to improve this controller. Let me show you the results of this first control solution. As I told you, we start somewhere here. As you can see, the initial condition is here. In red, what you have, this is the periodic trajectory that you want to follow. I want to follow this predefined trajectory. Theta 1 on the angle of the pendulum. We start from here. As you can see, look here, we converge. And we have a perfect tracking of this degree of freedom. Since it is activated, there is no problem. However, this is the speed also. So on position speed, there is no problem. We have a perfect tracking. And in this case, what happened on the internal dynamics, this is the control input. This is the speed of the inertial wheel. As you can see, we start from here and we converge to a periodic trajectory. And this is the solution which helped the system to stabilize the zero dynamics. This is the parameter P, which is computed by optimization. At the beginning of each cycle, we do an optimization. Yeah, if I apply this control input, what happened on the zero dynamics? And I do an optimization, and the best parameter was this value. And with this value, I can stabilize the system. It means that the zero dynamics is stable, the activated part is stable, and this is the phase portrait. So we start from this initial position, we do like that, and we converge to a stable limit cycle here. And the control input also is periodic. So this is simulation results. Look, this is simulation results. And keep in mind what I told you at the beginning. There is a gap between simulation and the experiment. Look to this curve. It's perfect. Look to the reality. It's not perfect. So there is a big difference between simulation and experiments. Look to the experiment, real life. You have noise, you have hardware, you have discretization, you have a lot of problems, and you can see them when you implement your controller. So the same here, we can see the tracking of the position, the speed of the angle of the pendulum. Look here what we can remark also. If you take the blue curve here, which is following the red one, it has a small noise. However, when you compute the time derivative, you amplify the noise. Look to the blue one of the speed, which obtained by numerical derivative of the blue one here, and it's noisy. This is also real life. This is the state, the phase portrait. We start from this initial condition, and also you can look here to this limit cycle. It's not perfect. Why? Because we have noise here, as you can see. This is the real life. The angle of the inertial wheel. This is the optimization parameter. If you have seen in this simulation, look, in the simulation it's easier for the controller to stabilize the system, but in experiment he has to do optimization and to change frequently this parameter to stabilize the zero dynamics. Now we apply external disturbance. We tried the scenario of external disturbance of this first solution. Look here, we apply an external disturbance here. We can see the effect on the speed of the inertial wheel. We can see the effect on the limit cycle. So we converge, and then this is the effect of the external disturbance. We can see it on the inertial wheel also, because this is the reaction wheel that tries to compensate for the external disturbance. It reacts here. The variation of the parameters that is optimized, and also in terms of control input here as tension applied to the motor of the inertial wheel. And the same scenario now with experiments. This is simulation, this is the experiment, the same remarks that I give you before. As you can see here, the limit cycle, we disturb it, we go away and then we come back. And then the second disturbance here, we apply 1, 2 disturbances. We have the first one here, second one here. We can see the effect of both disturbances and also the effect on the inertial wheel motion and oscillation. And as I told you, very, very important to do experiment, because you will see all those aspects that you cannot see when you do simulation. When you do experiment, you will detect a lot of problems and a lot of issues. And this is a persistent external disturbance which is applied here, a mass that generates a torque, and as you can see, look here how it converges to this limit cycle. This is the tracking of the 2 degrees of freedom actuated. This is the N actuated, and this is the actuated. The inertia wheel, and this is the parameters. Here we use 2 parameters to be optimized, P and delta, in real-time computed and the control inputs. And the same scenario now in experiments. It's, as you can see, much more complex. The effect of the disturbance here, and the change of the parameters. And let me show you the video. So now the video of this nominal case plus external disturbance inflection. And to do the oscillation, the limit cycle duration, as you can see, look, the inertia will try to rotate, to move like that, and to go back, he has to change the direction of the rotation to have this oscillation around the equilibrium point. And so we converge on both the actuated and non-actuated degrees of freedom, and we try to apply the external disturbance. Nice. This is the other scenario where we use this estimator of the external disturbance that we have added to the proposed controller to improve the performance, because we try to estimate in real time and compensate for this. And the same scenario. So as you can see, the periodic motion that we generate, and also the behavior of inertia wheel that change the sense of the rotation depending on the trajectory. Nice, and then the last solution, we proposed another solution, and at this time, this solution is based on model-free control, and for this time, we did the same idea as previously, but we did in another manner. So the feedback tracking controller, we designed the first model-free controller, and the second model-free controller, it's used to compute the best parameters of the reference trajectory. It's the same as previously, but we used these 2 model-free controllers. And look, for the under-actuated system, we need 2 controllers to stabilize the system, because we have the actuated part and the zero dynamics part. This is why we needed 2 controllers. And some of the results, this is simulation as a result. We converge to the desired trajectory, we apply external disturbance here, you can see the effect here, here you can see the converge to the limit cycle. This is simulation. And the same as experiments. And you can see the experimental results, the tracking here, the effect of the external disturbances applied here, 2 external disturbances, here and here. And a video that shows you this. We call it a dual model-free controller, because we designed 2 model-free controllers to stabilize both the actuated part and the zero dynamics of the system, and we apply external disturbances here. As you can see, that may affect the rotation of the inertia wheel to compensate for this external disturbance. So this is the scenario. So I show you 2 solutions. So the stabilization and the limit cycle generation with different kind of solutions based on model-free control and state feedback linearization. And let me conclude this second lecture. So here I try to introduce this problem of control of under-actuated robotic or mechanical systems, and with that we can consider as complex robotic systems, as explained from the beginning. So those systems have less actuators than degrees of freedom, and we have been interested in 2 problems, the stabilization problem and the limit cycle generation problem. To resolve both problems, so we have to deal with a lot of challenges, like the highly nonlinear dynamic problem, the coupling between the degrees of freedom, the non-minimum phase feature of the system, because the internal dynamics is unstable, and we proposed different solutions for stabilization and limit cycle generation, and we validate in simulation and also through real-time experiment. The same links as I gave you in the previous lecture. Let me stop here, and thank you very much for your attention.
Thank you so much for your second lecture about control challenges about this kind of system. So we can start the question and answer section. So if you have a question, please raise your hand and please bring your name and your institution first. I suppose we had some questions because we had a lot of students from control theory from La Sala and another institution.
Yeah, please.
Thank you very much for the lecture. Quite interesting. My name is Javier Molina from La Salle, Bajío. Sorry, I didn't introduce myself in the last lecture. So I have two questions.
Yeah.
The first one is, what about with the swinging up? Which one is the control for swinging and then for keeping the inertial wheel in the top position? Are you using two different controls? And my second question is about the hardware. What kind of sensor are you using? Yeah.
Okay, nice. Okay, very good questions. Let me answer both questions. So, concerning first question, the swing up. So here, since our system, let me go to the picture. I will show you. So we didn't do like in fact a swing up because we didn't start from this position, because mechanically the system was in this position. Understand? This is position. If it was like that, we do swing up to go. But here we were close to the vertical, because the difference between this position and the vertical, it was like 8 degrees. Understand? So we moved from this to we were not here to move. So it was not swing up. It's like a swing up, but we didn't switch between two controllers. It's only our controller that we apply, because we are close, 8 degrees. We apply directly control and we can do the motion. But your question is very interesting, because in the literature, a lot of people, they propose solutions to do both. Stabilization and swing up. For the swing up, they apply a linear control to move from here, sometimes the oscillations like that, until when they reach, they will be close to the vertical, the unstable equilibrium. Around this, they switch to the linear controller. A non-linear control to go here. I am close to the vertical, I switch to linear one and stabilize. So in our case, now we are close, directly we apply the controller. So this is the first question. The second question, it concerns the hardware. A very good question. Actually, we have two sensors. Let me, yes, that are here. Here, the inertial wheel is equipped with this motor to control the rotation, and there is here an encoder. So we measure just the angle of the inertial wheel, just the angle. And we measure the angle with respect to the vertical using this inclinometer, this sensor. So we have two measurements, two positions. However, yes, you are right. In the experiment, we need the state, position speed. So we need position speed of the inertial wheel, position speed of the body of the pendulum. So for the speeds, we compute them using numerical derivative directly. So this is why, if you check the curves, you have seen that we have noise here, like for instance here. Look, this is the position, this is the speed. We compute that numerical derivative and we amplify. Here we amplify the noise, but it was okay in our case. But if it does not work, we have to find a solution to this problem of amplification of noise. Yeah, other questions?
Another question?
Yeah, please, Jesus, yeah, there.
The other microphone?
The other microphone? Rafael, where is?
This is
Jesus from Centro Geo, Querétaro. I have just a question.
Yeah, please.
From your slide 33, please. Could you put your slide?
Slide 33?
33, yes. What happened? What happened with the centripetal force?
With what?
What happens with the centripetal force with your input?
Yes, it's this force that will generate a moment here, a torque, that will be used for the stabilization. If you go back, look to the, when I apply, yes, look here. It's this force, okay, this centripetal force, right, that will generate a torque here. And using this, you can stabilize. If there is no effect of this force here, you cannot stabilize the system, you understand?
Yes, right. Maybe for your results, your real results, this is the cause, the oscillating, your real results. Is generating oscillations.
For which case? The stabilization?
For the stabilization with your real results.
Here. Here we oscillate slightly at the beginning, then we stabilize the system.
Right. For the next one, for the lab test, when you increase, when you increase your
here, for sure. This is a persistent external disturbance which is present all the time. So inertia will try to compensate. But when you try to compensate, you rotate. And look here, you rotate around the volume. So you accelerate and decelerate to compensate with this. This is why we have this oscillation and its effect on the angle. So it's not stabilized perfectly, but it's stabilized around zero.
I think it's inferred another force by the centripetal. When you increase the speed, the kind of a sliding mode, it's generating a shattering. A shattering is the situation or something like that. Maybe for oscillation. Maybe it's for adding you the noise parameters, or include this kind of force, maybe.
The problem is how you can include it. This is the problem. You understand? Because actually what we consider in our case is that I explained, if you are rotating, it's equivalent to a force in this direction and force in this direction. And it generates a torque in this direction, and they compute both, so the gravity and the two effects of these two forces.
When you increase your speed, it generates another force.
Yes, we use the speed.
Right.
Yeah.
But the force appears in the maybe in the perpendicular plane.
Exactly. This is what we did.
Right.
It's perpendicular here and here. If you have no rotation, you have force here and force here, and you compute the moments here. However, what we compute in here, so it's a theoretical model. So you understand?
Right. This force generates for the from one side to another side. Maybe it's also another parameters or function to affect the dynamics for the movement.
Yeah.
Right. Maybe it's a comment.
Yeah. Nice.
Right. Thank you.
Thank you.
Hello, good night. Welcome back everyone to the last event of the third summer school on control of complex robotic systems. Tonight we have an exemplar person here. Dr. Mauricio Corona is an alumni La Salle and a distinguished graduate of La Salle in Mexico University, where he earned a bachelor's degree in information technologies, a master's degree in information technologies for business management, and also a PhD for business administration. He is the chairman of BP Gurus, a company focused on digital transformation, IT service management, artificial intelligence, robotics, big data, RPA, cybersecurity, blockchain, and emerging technologies. Dr. Corona is an internationally recognized ITSM professional, senior consultant, keynote speaker, and one of the lead architects of ITI L4, and his current work connects businesses transformation with advanced technologies, including robotics, bots, robotic process automation, and intelligent automatization applied to service management, operational efficiency, digital processes, and organizational innovation. Please welcome here.
Hello everyone. Good evening. How are you doing? I think it's a challenging session. The last session of the day is always challenging, so let's see how it goes, and let's try to get your attention in order to move forward with this topic. When I was talking with the people in charge of this agenda, we were discussing about the challenges that we have always in research, especially in scientific research. That it is that, well, most of the products that we build, normally they do not land into the business side. So it is always challenging going from lab to market. So this is why we're going to discuss, well, what have we done? What we have been doing since I founded the BP Gurus company. BP stands for Best Practices. And I founded the company 15 years ago. So it has been quite a journey. We started, well, the heart of our company is to advise companies on all of the digital transformation side, but we are always focused on best practices, international standards, and those kind of things. So what we do is we collaborate with international organizations, develop these standards, and then we were in charge of bringing those standards mainly to Latin American market, but sometimes to other parts of the world. So 7 years ago, I started an idea, which it was, I had a company, it was a big financial company. So the innovation director asked me to have a meeting because he told me that he had an idea with a humanoid. And I said, well, we do not do anything about humanoids, but for sure we can help you to address the idea that you have in your mind. So I arrived at that meeting and the director said, Mauricio, I think that you're not following me because I already bought a robot. It was a Japanese robot. It costed around 45,000 euros. And it arrived in Mexico. It was 7 years ago. Landed in Mexico, and they opened the box. And after that, they said, "Now, what are we going to do with this?" So it was stored in the luggage area. And then he said, "Well, Mauricio, I need to do something with this robot." And then I said, "Okay, I think that it is time for me to start doing some research on the robotic side." So I started traveling, visiting robotics and AI factories in Asia, Middle East, and in Russia specifically. And after that, then I said, well, I think that the best hardware that we can find is from China, but it was only on the first development. It was just taking care of the hardware, selecting or picking the exactly devices that we wanted, bring the devices over here, and once that they are in Mexico, it is like we need to start from scratch because normally the way that they assemble the parts are not right for our market. So we started doing some, after that research, we started doing some testing. We started working with several humanoids. And over here we can see, for example, this is a service delivery robot. And we were in pandemics. So after pandemics, we launched that line of business on 2019. And 3 weeks later, the pandemic came. So every single idea that we had on launching this line of business was just was rubbish. So we started again, and then we said, well, we have several kind of robots, humanoids, but we have a delivery robot. It is pretty much this box, only this box. Down here, it is like the kind of robots that the Amazon warehouses has. And then we said, okay, some people are looking for UV laser in order to sanitize every single room. So we adapted on the top, on the back you have UV lights. So we can actually, that was our idea of helping some organizations with the COVID and the pandemics. And on the other side, we started using this delivery robot for some hospitals. So while we didn't know exactly how dangerous was this virus, nobody wants to touch anyone infected. So we use this robot for delivering food and medicines to the people who were infected, mainly hospitals. And then we started moving forward with other types of robots configuration. What you can see in the chest, it is very important for us. What we found is that the screen that you see here, it is an Android tablet. It's pretty much, this looks like a TV because it is a 42 one, but it is an Android tablet, and we found that those were very, very important because we started developing some neural language processing services, but once that we deployed that on the outside, the noise was very strong, and so the people weren't able to communicate with the robot because of the external noise. So we found out that we need not only neural language processing, but other type of devices and technology in order to interact with the people. So we worked with these models, And then we use those to communicate, and then we start doing some interviews and things like that. But everything relies on hardware. And to be honest, what we have found is that there are some organizations that are claiming that they develop handmade in Mexico, robotics handmade in Mexico. That I think I have always think that sounds very romantic. It is interesting, but I haven't found yet any robot who actually does not have a chip, especially from Asia. It is impossible. So what we found is that, okay, we can start doing some testing. So I conducted another research, and what I found is that the devices that I was able to get from 2019 to 2020 was completely different. So the speed of the pace of innovation that I found on the robotics industry was massive. And to be honest, at the very beginning, as you can actually see, all of the robots were just, yes, we use LiDAR sensors in order to move autonomously on the places that we are, but all of those have wheels. And to be honest, on 2020, I said, I will never be able to get a humanoid who can actually walk, because the complexity of walking is much more higher, and the more complexity we have, for sure, the more expensive. So it was interesting to see that now we are able to have several humanoids that can actually dance with people. So I didn't get a video of that, but it is interesting. In only five years, we were able to afford one of those hardware. You know, it is very interesting, because that is something that is telling us that, especially for Mexico, we are very privileged, because we have access to plenty of technology, and the cost is now affordable. So it is even for the universities and the scientific centers, with the budget that they have, now they can actually build very interesting robots that can actually meet the demand for real businesses. So we focus a lot on this, on improving, on understanding how every single model works. For sure, we built our stack, and after that we started with improvements. Now we have the same type of robots, but they are totally different for sure than it was 5 years ago. And what we found is that now we are able to get plenty of information from the robots. Every time we use the robots, we can get plenty of data. And we develop a whole team on the scientific side. So we have some data scientists, and they for sure started working on how can we collect the information that we get from the robot. It could be pictures, videos, it could be for sure the voice when we're interacting with them with neural language processing. And it could be plenty of types of and formats of data. So what we are doing right now and we are working is we're focusing on the upper level, that it is how we can learn and optimize the robot by using their own experience. So we are actually working on that. And what we found as well is, okay, the world nowadays, and especially on every single line of business, as we can see, there are plenty of options with AI models. And I have always said, well, for now, I can even enable a large language model in my robot, and the type of conversation that we have nowadays compared to the one that we had on 2020, 6 years ago, are completely different. But then we said, okay, there are plenty of applications, so let's step aside from the software side, and let's just focus on what can we do and what are the real use cases that we can actually work for every single line of business that we are seeing here. And we found out that well, we have plenty of options. We haven't explored pretty much, I think that only 20% of those sectors. So What we found is that there are plenty of opportunities for the robotic side, especially for the humanoids. As you know, there are plenty of type of robots, industrial robots, that I have always said that Mexico is really good on industrial robots. On the 80s, we had plenty of factories, especially on the automotive industry, and we have been doing very good and very successful on that side. And for sure, those industries, they still have these robots, but they are much more smarter. And when I say much more smarter, is because maybe they have the same chassis, but they added some sensors, and with the sensors, they added some collaborative robots, and now they are doing things that, for sure, they didn't think it would be possible 20 or 30 years ago. So there are plenty of things that we can do, but especially on the humanoid side, the use cases are increasing. We can actually deliver services that the business on the business side they are really interested. So what the main issue we have found, the issue is that if we follow the path, the certification path on the machine learning engineer, for example, this is how it looks like. So it is quite difficult. The head of our robotics department, he's a computer scientist and cybernetics from here in the university. But it is tough to get that kind of people, and it is tough, even tougher to retain those kind of profiles. So it is very challenging. It's not only about that we should work on the lab with these robots, but we need to think how we're going to deploy these robots in the real life. And what we found is that very few companies are willing to invest in buying robots. So other than scientific labs, that they are for sure interested in working every single day with those. But on the real life, they said, okay, it is way too expensive to buy a robot, and then on the business case, you need plenty of money, because there is something that is called the total cost of ownership. So if you think on how much money do I need to invest in order to have or to retain or to obtain more value from one technology, well, it is tough, because the humanoids needs plenty of service support, and that is expensive. So this is one of the issues that we have found. On the other side, it is like, well, how can we enable some algorithms and some machine learning applications that can actually help us to bring more information and to deliver more information to our customers. And we have been working on several proposals. This is just a layer from a monolithic data platform that the team is always trying to use and to exploit. This is something that we can actually use without the robots, which is interesting, because you can actually deliver, or you can build a robotics stack that can actually be exported to just software, and start working with software, and we just train some algorithms and then deploy those algorithms in the industry, and they will pay as well for that. So it is a good laboratory. What we found is that robotics is not only valuable because you have the hardware, you have the software, but it is everything that is around the line of business of robotics is interesting, because you can actually learn from the robot and then deploy into the actual environment on which you are working. So I really like this slide. It is a very comprehensive way of understanding what the customers have been looking for. And sometimes when they ask, they contact us and they say, hey Mauricio, I want a robot, they doesn't even know what they want from the robot. So it is for sure the experience, the wow factor, and we have ended up working with plenty of CMOs, with chief of marketing officers. They said, okay, I want this wow factor in one of my product launch events, and it works really well. But there are other organizations that are starting to think that they can use the robots for much more than that. just appearing the robot and let's say, wow, it's really nice. And what we have been doing is we are working on having a much better way, and I will say a much more secure way as well of handling the information. It is very sensitive information, so just imagine that you have a robot that is actually recording everything in an in-house event in a company, so you actually have pictures, videos, conversations. So security is something that we really take care of, and considering what they want to achieve, then we make some calls, and sometimes we said, okay, we are not going to record anything, or sometimes we are going to record just the voice, or just the conversations, or only the images, in order to provide some kind of analytics to our customers. So what is very interesting here is that from one product that you have, that it is the humanoid, you can actually build on top several services. So you can actually have several types of analytics and deliver those analytics to the customer after 4 hours, 6 hours, or maximum 8 hours. That's how long the batteries last. And there are other challenges as well. Sometimes the robots are in Cancun in an event, and it is very challenging. Logistics are complex because batteries can't go on a flight, so they have to go all the way to Cancun. So it took us at least 2 days to arrive to Cancun, 2 days to come back, plus the days that you are going to have the robots over there, and additionally the engineers behind the robots. So it is complex. This is why you need to address and to focus on organizations that are really willing to pay that investment, because it's not easy at all. So on top of the data, what we have been working is on delivering a variety of applications. It all depends on what does the customer wants. Because we can have, for example, if you have over here cognitive services, so you have, for example, perception, interacting with human, acting, thinking, perceiving, everything we do is everything through actuators, sensors, mainly hardware. And when we are using this hardware, we are capable of doing some things, like responding, like decision making, like bringing data in order to store that into a data lake and then do some machine learning, natural language processing, computer vision and hearing. And from there you can actually deliver plenty of value, and you can actually sell every single aspect that you want to, that the customer want to experience with the robot, because from responding you can actually offer speech synthesis and natural language generation, robotic process automation, control of other systems through APIs. I'm pretty sure that you are aware of the RPA, and in the RPA that is very interesting, because sometimes customers want to address something with their processes, and then you say you actually do not need hardware. You need a robot, yes, but that robot is just a license. It is software. So you actually buy a license, you have a robot, and then you automate the processes. So it is interesting. From here, you can actually offer another type of solutions. And on the decision making, we have case-based reasoning, expert systems. On the machine learning, that is where we can actually go over in the Gartner data analytics graph that we saw, from supervised learning to recommended systems. For sure, we can actually do plenty of things. At the very beginning, the robots were constrained to only speak Chinese. So it was like, there's no way we can use this in our market. So after developing several things, we were able now even to do some machine translation. So early morning, I deliver a conference in Expo Banamex. They are running a electronics and tech conference, and I was surprised because every single stand that were there, all of them were Chinese. So I saw maybe a couple of USA brands and maybe another from Europe, but 95% of the stands were from China. And there were plenty of people that actually only speaks Chinese, Mandarin, and a little bit of English. So it was interesting. And once that you have one of these robots, you can actually address those issues, and you can just move forward to the next stage. And well, computer vision and hearing, it's very interesting because starting from facial recognition to image, optical, OCR, handwriting, speech recognition, you can actually build several dynamics with the robot, because as soon as the robot just identifies your face, you can actually ask the robot to do a specific task, and it will be very customized, so the experience changes a lot. And what I say, this is what I really like from the humanoid side. When you are working with humanoids, you have to use several cognitive services based on several algorithms, based on several products and hardware, that they must act together and at the same time in order to imitate the human being. So it is very interesting, because if the robot is not executing every single algorithm in an orchestrated way, then the experience will go down, and the robots will not exactly be able to, we will not be able to go into the real industry, because it will do not have real case scenarios. So what we have seen as well is that we are moving forward. Technology for sure is quite tough. I know that you really understand that conducting research in this area is very difficult. Why is that? Because while you are just testing one theory, the world has changed. And we have new circuits, and we have new algorithms and new hardware, and it is quite complex. But I think that the bad news for us in the scientific side is that the pace of innovation will keep increasing. So I said that from the scientific side is, or we become more agile on running our scientific research, or we should change the topic on which we are researching, because it's not enough. It's not enough. Maybe you will finish you will have the outcome of one of your research in 1 year, but the world is totally different. And there are several technologies. I think that I have over here some technologies that we have been seeing that the industry is using, and every single technology is having a straight impact in robotics. So it has been tough to understand the previous, from 2025 until 2025. It was pretty much on cognitive modes. We saw natural language processing, maybe 6-7 years ago in our phones. It was pretty much an affordable technology. But then trying to interact NLP with computer vision, and then pattern, and then reasoning, then that was the toughest part. But we started with a root-based inference, then supervised learning. And from 2025 till date, it was pretty much on unsupervised, and the learning was narrowing. It was narrowing. So every single domain is evolving and is maturing much more faster. And the hardest or the challenging part after this is that it will be much more on self-aware and supervised learning. So we have seen several demos, like you are using one Gen AI application, you start, this application is starting to interview with another application, and they can actually have a conversation and build some knowledge, and it is just two LLMs working and interacting together, and that's it. And it is impressive, because sometimes they arrive into really interesting conclusions without human interference. So it is interesting. So it is very challenging for us in the research side. So these are the most used algorithms that we need, that our data scientists have. The background is important as well. For sure engineer, but I think that the most data scientists, the background is more on actuarial sciences, mathematics. Those are the guys who actually are helping us to really understand, considering the type of data that we have, structured, unstructured, what does the customer wants to achieve with that, then well, they actually make sure that this could happen. So it is interesting. But from the business owner's perspective, from my own perspective, I love and I really understand about the research, considering the PhD that I did like 12 years ago. But what I found is that we can actually work a lot on all of the things that we are very passionate about, that, especially in researching. But if we do not provide value, then nobody will buy our projects. So the value is always at the center. On top of the value, we must think, okay, how can we deliver actual value to our customers? And from there, it is thinking on the ecosystem. We should always work, we must work in an ecosystem that is already out there. So we need to find the people, the right people and organization, the right information technology, the right processes, the right partners and suppliers. So we have been deploying some use cases on, for example, on breweries. They are at remote locations, and the customer says, "Hey, Maurice, I want that the robot shows the whole process of how we brew beer." Okay, we send the robot, we configure everything. They are just ready to go, and after a few hours, telecommunications goes down. So then you find out that, well, telecom has nothing to do with my business, or if I do not make sure that that ecosystem is ready for getting my hardware and my products and services, then nothing will work. And on the other side, after pandemic, we hasn't had a single normal year. It is after pandemic, and then it was war, and then it was half of the world were changing leadership, and so we always, we are at least once a year, we're always conducting something that is called the Bestel analysis. So we need to consider politics. Now you imagine how much money do I need to invest in bringing new hardware from Asia compared to 6 years ago. The amount of money is totally different. So the budget has to be different, and there are plenty of uncertainty. So we need to understand politics and see if we are switching to bring hardware now from the Middle East, or maybe bringing hardware from the US, or if we bring the hardware from the US, it's going to be way more expensive. So is the economy or the local customers are willing to pay those decisions? I don't know, but it's something that we must consider. On the other side is the economics, the social, the technological, the legal, and the environment. So it is called the Bestel analysis. It is very interesting. It has helped us a lot to understand if our research idea and then our product development will actually be has some probability of being successful, and to from build to test to deploy, plenty of things happen, and especially with advanced technology. So what I always say to my team is, okay, you have to have the goal very clear at the very beginning of your project. If that is not the case, then we're just moving forward and let's see what are we doing, and then we buy one specific hardware, and 2 months later we say, I think that I made a mistake. I should have waited 15 more days, and maybe we will have a new version of that hardware for the same price. So those kind of things are very important, and sometimes when we are conducting research, we do not consider those variables. We are only focused on the topic, the main topic that we just thought that would work. And I have been working and studying with some guys at the MIT, and one of the main discussions that we have is what technologies are changing the world right now. And those are the technologies, those are the outcomes from those discussions. And we have IoT, and I will say that on our side, it is the IIoT, it is the Industrial Internet of Things. Like, just place a sensor and everything will be smart, and you will get plenty of data. And then the challenge is, how are you going to handle and manage and take care of that data? What way? We have this IoT, we have plenty of wearable devices that are giving us a lot of information. And that information is very interesting because you can actually put some asteroids on your research. If you just add some sensors, and it will be like, no way. Sometimes we struggle a lot on the research side of getting the data, right? So, okay, you just find the right partner or find the right customer in the right industry, ask them to put some sensors on it, and you will have plenty of data. For sure, mobile devices, but everything that I said, okay, when I talk about the digital transformation, when I mention the word digital, I mean 4 things. The first one is sensors, smartphones and everything. The second one is telecommunications, that I was mentioning you previously, that this is very important. The third one, it is cloud computing. On the cloud computing side, we need plenty of infrastructure in order to run and to achieve what we want. So without cloud computing, it will be impossible. So we must focus on that. And the fourth one is on the machine learning. For sure, plenty of big data analytics. What I have seen from my customers, yes, the wow factor is at the beginning just because of the hardware. It is moving and it is talking, it is impressive, but that good impression will last 4 hours. And after that, the customer will ask, and then what? So, well, I need to get good data. On the other side is cognitive AI, and especially for the humanoids. We are just imitating the human structure, so we need to think of always on cognitive services. And that is why I was telling you that cloud computing is very interesting, because we can actually find plenty of cognitive services already in the several cloud platforms, so it's interesting. Robotics, any type of robotics, okay, for sure. Additive manufacturing, that is very interesting. I have a discussion with one professor at Kellogg in Chicago, Kellogg Business School, and he has a theory that every single logistic point will be shortening as time goes by. And in the near future, we will have, yes, Home Depot, but Home Depot will be completely empty. And instead of everything that we see right now in the Home Depot, they will have 3D printing machines with additive manufacturing. And you will log into homedepot.com. You will have a design studio. You will design your furniture, the color, the size, the material that you want. You just click print, pay for it, and then just move to the Home Depot to get your furniture, or if it's too big, it will just arrive to your home. Everything will be customized. And that is, he has the same theories with medicines. There will be no pharmacies, no drugstores. So you just, okay, this is my prescription, print. The additive manufacturer will print the prescription, and that's it. It will be delivered into your house in the same day, or if it is now the Amazon new service, like 30 minutes or so, something like that, well, we will have that. So everything will be shrinked, and everything will be printed, even food that now we have some interesting protein that can be actually printed. So So it is very interesting because if we lose sight of these new technologies and these new trends from our researchers, then once I finish the research, it is like, okay, but did you know that this can be done actually by this other technology? So wouldn't it be more interesting to interact or to interconnect that technology with your technology or the proposition that you're having? So in blockchain we have done really nice things. Other than cryptocurrencies, that for sure I'm a big fan of that, but on the real value proposition, we have found, for example, in the Middle East, in Dubai, we worked with Carrefour, and exactly after pandemics, people were concerned about what they were eating. It is like, okay, if I have a vegetable, I want to know where is this coming. So with blockchain, we helped Carrefour to develop. We used an IBM partnership. They have a really nice permissioned blockchain, and it was traceability. With this traceability, just text, and then you said, okay, this is the information of the seed, this is the information of the ground, this is the information of the location, how much water have you put on that, how many wastes on pesticides, everything, and then you track just with blocks. And after that is when you pick up the lettuce, who were transporting the lettuce, under which temperatures, when it arrived to a central market, and then when it arrived to the corner market, and then when you arrive there, you bought the lettuce, and then you just scan the QR, and you have all of the information. It is mapped, and you can actually do traceability of everything that happened from the seed to your plate, everything. And it's very interesting. So blockchain is very powerful, and it provides you a lot of information. It is structured data. It is very easy, very comprehensive, and once that you put this data into a data lake, you can do actually really interesting things on running some prediction with the data. Quantum computing is very interesting. 6 months ago, I was delivering a session at the National University now, and we were the whole Congress were around quantum computing on the development life cycle. So we discussed how quantum computing will enable us to do things 10x, 20x, 100x faster than we do right now. So if we are struggling with the CPUs, GPUs, or every single device that you want to use in order to process the data, once that we have quantum computing, it will be very interesting. I don't know, have any one of you have done something with quantum computing, researching? Wow. Even if you go to IBM, I think that IBM is really good on this one. I have mentioned IBM. It is weird. I never mentioned IBM, but it's twice. But IBM has really good resources, and you can actually do some tests with your data on the IBM webpage for free. And after that, for sure, they will start charging you. Quantum computing is almost there. And when I say it's almost there, we can actually do something with them, but it can't be used broadly. Why is that? Because it's very expensive. But it's going to arrive sooner or later, and I think that it's much more sooner than later. So it is very interesting, and for sure, well, social networks, we have seen the power that we have in social networks and understanding behaviors during across these networks is very interesting. VR, AR, mixed reality is very interesting, and autonomous machines for sure. And I think that we started 4 years ago. We can actually drive autonomously from Mexico City to Cuernavaca, not touching the wheel, nor the accelerator, nor the brake, and the car just go on back. So it is very comprehensive, and that talks a lot as well from the Mexico perspective, that we have plenty of competitive advantages on that side. We have access to the most advanced technology, which is affordable, we're in a much better position than in the event in the morning. There were people from Uruguay, from Honduras, that they were saying, Mauricio, but we do not have that in our countries. So there are plenty of things. And this has been there for a lot of time, the aerospace. In Mexico, we have really nice clusters on the aerospace. I remember working with Honeywell 8 years ago, near Tampico or places like that. So in aerospace, we have plenty of technologies, but the products and services that are starting to be built on top of that technology are something really new for us, In the Middle East, in the most developed countries, aerospace is the thing 3 years ago, 4 years ago. AI was 10 years ago, so AI, they are like, if you arrive and you say, okay, let's use AI, everyone there is like, it's just like if you say, let's use internet, it's pretty much like that. But aerospace is very interesting, so I think that there are several promises, some of them sounds like science fiction, but one of the things that I always ask myself is, if I would have asked me if the economics in 2026 were going to be like that 2 years ago, I would say that's science fiction. So we are actually living science fiction, so we don't know what is reality and what is not. So it is very interesting, and that is why I think that we must take every single technology, we must have some respect for every one of those, for the promises that they are stating, because most of them are actually delivering what they promised. So that is interesting to see. And I would say that what characterizes the robotics business model, I always use a canvas. This canvas is based on Dr. Osterwalder. He's a Swiss guy. And pretty much every single business in the world have used this canvas. And when I am working with technology, it is like, okay, the next step is how am I going to commercialize this? How am I going to bring this to the market? And I always use this canvas. It is pretty much like, okay, just stating or be clear about who your customers are going to be. And I have been pivoting my line of business, because at the very beginning I was telling you that I was thinking that we were going to sell the robots, and after we sell, we will provide services and service support, and we will get great money from that. Well, that didn't happen. First pandemics, and the other one is because it is expensive. So we pivot the line of business, and we moved to some a business that is called robots as a service, when you can actually pay as you consume. If you want one robot, just pay for an hour, pay for 4 hours, pay for a day. We have had customers that actually pays for a 1 year robot, so they have 1 year the robot in their premises, and that's fine, totally fine. So my market segments changed completely. Now they are marketing areas, customer service areas, events. They rent robots a lot, because you have 100 stands, and people will always go for the stand that actually has something new. Robotics is very interesting. On the other one, it is like, well, how are we going to arrive there? Pretty much on a B2B. This humanoid side is not a B2C business, for sure. The value proposition is range of models, flexibility in usage and period, robot customization. Every single brand who hire the robots ask for some customization. So we have the skills, we have the capabilities, we have the team, we actually deliver that as the value proposition. And for sure, in order to deliver that, you need the key process and resources, like data scientists, data engineers, business experts, because you need to understand what they are trying to achieve with your robot, especially an event or even in their local business. We always need to find key suppliers and key players in the robotics industry. And like I was telling you previously, I work in several AI and robotics clusters across the globe, and I think that 1 year you will actually see a lot, one type of robots, but the next one, it will be another brand. So you always need to find the right partner, and for me it was at the very beginning one guy from Japan, and then after that Well, I always wanted to have a Boston Dynamics. Have you seen Boston Dynamics for sure? But they broke and they sold the business to a Japanese company. So it is interesting to see. They have, yes, and I said, well, those guys have one of the best robots that I have ever seen. On dexterity and on degrees of freedom, the best robot that I have seen is from the UK. So it is a British one. It does not work. It is just, it has legs, but actually doesn't work. It has everything from, I don't know how many degrees of freedom, maybe 30, 40, 50 degrees of freedom. He can actually do yoga movements, and that's from the UK. Or after that, where you are actually seeing some robots, plenty of robots in Mexico from Unitry this year, especially the one who actually walks and dance and do ninja movements and those kind of things. It is very affordable, but I'm sure that the next year we're going to see much more players in the scene. So it's going to be interesting. So the key partners and supplier from Chinese manufacturers, financing, cloud services, the three main cloud services that we have, all of those are very comprehensive and cost effective. And the business model works like this. Okay, you need resources, you need to get revenue streams from every single project, but you have a cost model. And if your incomes are not higher than your outcomes, then it's not going to work. And it could be a great idea from the scientific research perspective. It is impressive, and you have outcomes, and you have articles published in very high-end magazines, and that's fine. But they will never see the light in the real industry. Which is not bad to have those outcomes, but it will be much better if we have a real impact out there. So that is exactly what I really like and enjoy from Harvard, from MIT, from those universities, that when you are actually talking with them, they are always thinking on being the next Facebook, being the next Tesla, being the next, I don't know, Google, LinkedIn, whatever. They are always thinking in that. And in order to achieve that, they move the research machinery in order to bring the product or service into the real world. So the value, well, it's pretty much like, why would anyone pay for your research? It is because you have resources that they want, and you have what they need. That is value for them. So you need to find the right customer as well, and even the customer could be somebody interested in research. It could be a good businessman who actually says, I am willing to invest $10 million in my innovation department this year. That would be a really good customer, really good one from the research perspective. So the customer is, what are you looking for? So we need to cover the needs, and for what he could be happy, live good, be free, whatever, any trigger he has in order to be willing to invest some money. So I think that this is a key component as well when we are starting our research. We normally do not look for this. It is like, who could be interested in that? We just are just thinking on how are we going to start running our scientific project, and that's it. Okay, as long as it is founded, we're going to be fine. But after that, things are getting much more complicated, and we struggle to achieve what we want. So the customers want to obtain value, and we must be the one who are actually deliver value to those customers. That's how both of them co-create value, and then the customer and the society actually perceive the benefit, the usefulness, or the importance of something. Just think about one product that is very interesting, that now it has been deployed in several cities in the US, like the robot taxis, the automated taxis. It could be a complete mess, but it looks promising. It looks like it's going to work, and it will create revenue, very interesting revenue streams. So how do we use the robots? For a lot of things, for conferences, that's the UV that I was telling you, for sanitizing rooms. This is one of the robots who were stay 1 year in one of the companies. This company is in the domotic business, so automating every single office or home, and the robot was one of the key things that they use in order to bring attention from their customers once they arrive to the office. On the interviews on several channels, we have been there. I think that those pictures are like 6 years ago or so. But it was very interesting. Yes, in fact, this is a fake mask. It was just, we programmed that. We were in pandemic, so we added a mask over there. And one other thing is that we have been contributing to education. That is very important. This is a Robocon. We helped to work on the first humanoid, the first robotics contest where we actually had people from across the globe, and it was interesting. And for sure, research on that is very important. This kind of delivery robots are very interested because we can actually do these kind of things. And well, we have some AI and robot case stories over there on that address. This is a case story that we did in Grupo Ángeles on the health system. So the robot was actually receiving you from the lift, from the elevator. Once that you go out, it shows you the way to the right room, and then introduce you to your doctor and assist the doctor, and it is very interesting. So you can actually work on very interesting case scenarios. So this is pretty much what I had for you. So I'm not sure if you have any questions. We have time for Q&A.
Thank you, Mauricio, for the presentation. You have some questions, comments?
Thank you for your talk, Mauricio. I'm Miguel Torres. I'm an economist, and I have a question. When you compare Boston Dynamics versus OpenAI or Tropical or whatever, for me, I think in principle it's more valuable a robot or a computer that makes something like a robot is more valuable than ChatGPT that answers very good questions, but that's solid task, so it only gives information. How can you reconcile Boston Dynamics not more expensive than OpenAI? With, for example, in principle, again, Boston Dynamics could add more value because it can make things.
Yes, it totally makes sense. I think that the key is that they are totally different businesses. And when I was showing one slide in early morning that I was telling, for example, ChatGPT it's not AI. If you say it's not equal to AI, if you see the layers of AI, so you have AI, and then you have machine learning, and then you have deep learning, and then you have generative pre-trained transformers, and then you have LLMs, and then you have products like ChatGPT. So if you're using ChatGPT, you're just using the power of that level from the whole AI. But what they achieved is that, just remember in the economic side, it is like if you can actually create a product that can be easily replicated across the globe, then you will be rich. And that's exactly what OpenAI did. So they start working and training LLMs as well as all of their competitions, but they were the first that said, okay, we have good maturity, and the main thing is that we can actually replicate easily what we have done. So they started, if you remember, with the easiest part of GPTs. The easiest part of GPTs is text.
Yeah.
They doesn't get into images, on videos, on audios. Those products came later on. But they said, okay, now we are ready for the most basic stuff. And they did that. They brought a lot of money. I think that they achieved the 5 million users in 1 week, something like that. And with that, they got plenty of money and funding, and that's exactly what they needed. After that, well, according to Elon Musk, they became greedy, and now they do not want to be a company that is actually helping the world without expecting revenue. Now they are doing. But on the Boston Dynamics side, it was like they invested a lot of money on research and development, and the type of investment was huge. I will say that the robots were really good, the best that I think that even the best that we can find right now on quality and everything that they can do, but they are expensive. So that is why they said, okay, we need to sell the company, and they got a big trust fund. It is a bank. I just can't remember what bank it is, but it's a Japanese man who actually bought them. And I think that that's pretty much, and that is the sad part of the story, because from the technological perspective, you have a much more higher quality and really good product, even much more scientific product. But on the other side, it is a much commercialized product that actually works. And well, now we have the story, and after that, the rest of the companies did a really good job, and they increased their capitalization billions of dollars. Thank you. Pleasure.
Comments? Si quieren pueden hacer.
I got another one.
Pueden hacer la pregunta en español si no.
No se anima.
Well, I have a doubt about the market of robots that you briefly said. Well, you said that many companies are implementing these kind of robots in, for example, the medic and market area, and I told you that. Do you think that there will be like a saturation of this kind of robot, like it's happening with the AI, that many companies are seeing that implementing AI in every area of their companies it's like a bubble that instead of having a benefit for the company will be like a economic loss for these areas that I think that it's more rentable hiring humans than buying APIs.
Yeah, great question. Well, what I think is that if you talk about specifically speaking from the humanoids side, it's not going to be enough. It's not going to be. They are complex and the use cases are reduced. But if you talk about the robotics industry, then I think that there is a high probability that the robots will be everywhere. And it is even now we are using plenty of robots, but we don't even know about that. And if we consider every single type of robot, like the RPA that I was telling, that the robot is equal to 1 license. So there are plenty of companies that are actually using robots in order to handle their processes. So I think that right now, plenty of organizations and we on our daily lives are actually using plenty of robots. So generally speaking, on the robotic side, it will keep growing and growing and growing. It will be sometimes in the cobots form, sometimes in the industrial robots, sometimes with humanoids, sometimes with software. But robots are here to stay. Yeah.
Thanks.
Other comment, other question?
Hi, thanks for the speech, first of all. And I was wondering if at the start of every business, there's the risk of failure, and particularly for the area of robotics, the investments, it's high enough to take like a risk very slightly. So the question is, apart from knowing like the market or what you were mentioning about the clients, the requirements of them, and so on, what else could you say that is important to take into account to reduce this?
It's very interesting. Yes, the first option is, okay, you need to know your market, everything that we discussed, but after that, well, what's the next step? And I will say, start small, think big. We need to start with something that we call the MVP, the minimum viable product. And from there, you do some testings, you see if you can actually deliver some value. If you deliver some value, instead of charging $1 to your customer, you will charge 10 cents, but you are starting to get some revenue. So start small and think big, and everything is iterations. I think that one of the biggest mistakes that we do while doing research is that we want the research to solve the world. And as you move forward, then you say, okay, that's very romantic. It doesn't work like that. So you need to start prototyping, going really small, minimum viable product. Then once that you have one achievement, then you build an additional feature, and then the next stage, and then the next stage. That's pretty much like moving on the agile way. You know, it is like build, test, deploy. If it works good, if not, you correct. Build, test, deploy, and then you go for the next one. So with that, you can actually have a much slower budget, slower times, reduction of diminish the time to market, and all of those variables. So it's very interesting. But yes, that's the other thing that I would say.
Is there anything like a methodology or something like that, like to try to predict trends? Or, for example, I was thinking about the slide that you shared about the different areas of additive manufacturing, robotics, IoT, and so on. So, for example, I could say, okay, I want to start small, but another question could be in which area? No?
Yeah.
But maybe, I don't know, there's like the prediction of the boom.
There is no methodology for sure, but I'm going to share with you what I do. I follow the stock exchange. That's where the money is going. That's where you can actually see what the market right now is getting value. And for sure, you have plenty of information, and from there you can actually make your own decisions. But it is an example. On last Friday, SpaceX was launched. It is now how can it be possible that one company that had just been launched is now the number 7 in capital assets in the world? It is crazy. It is 2 days because Saturday and Sunday stocks doesn't work. So it was Friday, Monday, and today they are the 7th biggest company in the world. That means that this company is getting plenty of support from the aerospace industry. So the aerospace industry will start to build completely new things, new stuff. And you have to be there. You have to be there. And if you start follow those companies, what they are doing, what their plans are, they always say that in advance, because if you're in the stock exchange, they commit with targets, not only on the financial perspective, but on users, on new line of business, and then you learn that someone bought Boston Dynamics, and it is, oh, that's interesting. So that's what I do, and that's the main pulse that you will have in the market, at least globally. But then you need to translate that into your country, your region, but you can start from there. Thank you. Is there any other question? We're good?
I have a question, because sometimes, like students, you see this very far from my project, my final project, and sometimes it's very important to hear someone like you that have vision, experience. What is your recommendation for them? So what is the first step in the master degree, in the bachelor? No?
Yeah, I think that the toughest part for me, for myself, it is to believe in me, to believe that I can actually build something that will change the world. We can actually do that. For sure, I am far, far, far away from doing that. But once that I understand that, I said, okay, you can always do anything. Even 6 months ago, hey, SpaceX is looking for engineers. Who wants to raise their hand? Just raise your hand. Send your resume. I have nothing to offer. No, I got but. There's no but. It's like just believe that you can actually change the world, and you can raise your hand, and you can go outside, and you can do whatever you want. It's just saying, yes, I can do it, and that's pretty much. And the rest then you will find out. For sure there are going to be plenty of mistakes, but committing those mistakes are the easiest part to grow and to learn and to move forward. And I think that that's pretty much one of the key things that I would say to myself 20 years ago.
Well, please.